Why does the universe seem tuned for life? And what does that imply about reality itself? What hidden balances, from magnetospheres to tectonic cycles, make worlds like ours endure? How do cosmic hazards and stellar life cycles remind us that habitability is both fragile and rare? When contemplating why the universe is hospitable at all, some thinkers invoke the anthropic principle. It suggests that the laws and constants we observe are those compatible with observers. In some versions, countless universes exist with varying parameters, and we inhabit one where stars, planets, and chemistry permit life. Others propose that a simulation, vast, intricate, perhaps created by advanced beings, could explain fine-tuning. Such ideas blur the line between science and philosophy. They encourage humility about our capacity to know ultimate reality, and prompt us to question which aspects of existence are contingent and which are necessary. At the level of detection, astrobiologists devise ingenious methods. They measure the ratios of stable isotopes, looking for patterns that indicate biological fractionation. They search for chirality, the handedness of molecules, which life on Earth expresses with near exclusivity. They examine morphological structures under microscopes for cell shapes or fossilized microbial mats. They track seasonal variations in atmospheric gases that could hint at metabolism. Each technique requires careful calibration to distinguish life from geology. As instruments become more sensitive, our ability to detect subtle biosignatures improves, expanding the range of environments we can analyze. Climate on a planet is a tapestry woven from stellar output, atmospheric composition, orbital eccentricity, and internal dynamics. On Earth, the faint young sun paradox illustrates the interplay of these factors. When the sun was dimmer, greenhouse gases like methane and carbon dioxide kept the planet warm enough for liquid water. Over time, photosynthetic organisms drew down carbon dioxide and released oxygen, cooling the climate and enabling the evolution of complex life. Glaciations and hothouse periods punctuated the record. Understanding these feedbacks helps us model exoplanet climates and evaluate their potential habitability. Information may also be stored in cosmic archives. The cosmic microwave background is a relic radiation from the early universe, carrying imprints of density fluctuations that seeded galaxies. Some have speculated about encoding messages in such ancient signals, though practical limitations make this unlikely. Still, neutrinos and gravitational waves propagate largely unimpeded across vast distances. They could carry information across cosmic epochs. Contemplating such possibilities expands our horizon of communication and underscores the ingenuity required to imagine what forms alien transmissions might take. The diversity of human languages offers another lens on communication. Languages encode unique ways of categorizing the world and structuring thought. Some emphasize relationships over objects. Others lack specific tense markers, but encode evidentiality. These differences influence how speakers perceive time, agency, and causality. Translating between languages involves more than substituting words. It requires cultural understanding. An alien language might diverge far more than any pair of human tongues. Studying linguistic diversity prepares us to confront the unknown. It also highlights the value of preserving linguistic heritage on Earth. Music offers a universal form of pattern and emotion. Across cultures, rhythms and melodies evoke feelings that transcend words. Music can be described mathematically as sequences of frequencies and intervals, making it a candidate for interstellar messages. The Golden Record included Bach and Chuck Berry, alongside folk songs from around the world. If we receive a pattern of tones from the stars, we might first treat it as data, but we might also consider it as art. listening with both analytic and aesthetic sensibilities could reveal structures that pure logic might miss. Psychological responses to the possibility of alien life range from wonder to unease. For some, the idea of a cosmos teeming with beings inspires joy and a sense of belonging to a larger family. For others, it triggers existential dread or fear of invasion. Fiction explores these extremes, from utopian federations to dystopian occupations. Examining our emotional responses can inform how we prepare for potential discoveries. It also invites discussions about xenophobia, otherness, and the need for empathy. The Fermi paradox may be as much about human psychology as about astrophysical realities. Speculations about cosmic civilizations sometimes invoke the concept of cosmic watchers, advanced beings who observe emerging intelligences without interfering, perhaps following an ethical code. This idea appears in indigenous stories and modern hypotheses like the zoo scenario. While there is no evidence for such watchers, the concept serves as a mirror. It asks how we would treat a nascent intelligence we discovered, whether we would guide or avoid contact. It also reflects our anxieties about being under surveillance or ignored. Imagining watchers encourages ethical reflection on power, care, and respect. Assimilation and exchange are fundamental to evolution and culture. Endosymbiosis, the process by which mitochondria and chloroplasts became part of eukaryotic cells, shows how cooperation can lead to new levels of complexity. In human history, trade routes and migrations have spread ideas, technologies, and genes across continents. If we ever encounter alien life, assimilation might occur through shared knowledge, intermarriage, or even hybrid organisms. Alternatively, exchange could be purely intellectual. Considering these possibilities challenges us to imagine relationships beyond conquest or isolation. As this part draws to a close, we feel the tension between completeness and continuation. We have traversed topics from ancient myths to cosmic futures, from chemical reactions to philosophical conjectures. Yet each subject opens into new questions. The journey is iterative, inviting revisiting with deeper understanding as knowledge advances. The next part will delve further into the uncertainties, the latest research, the speculative frontiers, and the human dimensions of the Drake equation. For now, we leave space for silence, letting the ideas settle like silt in a river before the next flood of curiosity. Cosmic hazards shape the backdrop against which life emerges. Throughout the galaxy, massive stars end their lives in titanic supernovae, flooding space with radiation and heavy elements. Rarely, hyper-energetic gamma-ray bursts sweep through like cosmic scythes, sterilizing planetary surfaces within their narrow beams. Closer to home, flares from our own sun occasionally disrupt satellites and power grids. Understanding these hazards teaches us about resilience. It reminds us that habitable worlds must weather storms far beyond atmospheric fronts, and that survival may depend on more than luck. Our planet is shielded by an invisible guardian, the magnetosphere. Generated deep within the liquid iron core, Earth's magnetic field deflects charged particles and guides them toward the poles, where they paint the sky with auroras. Without this shield, the solar wind would strip our atmosphere and expose life to harmful radiation. Mars, once wetter and warmer, lost its magnetic field and gradually became an arid desert. The interplay between planetary interiors, magnetic fields, and atmospheric retention illustrates the delicate dance of factors required for long-term habitability. Geological processes also act as the planet's long heartbeat. Plate tectonics cycles carbon between the atmosphere, oceans and rocks, regulating climate over millions of years. Without subduction zones and mid-ocean ridges, carbon dioxide could accumulate unchecked or be locked away entirely, leaving the surface either sweltering or frozen. Continents drift, collide and break apart, reshaping ecosystems and promoting biological diversity. Mountains rise and erode, rivers carve valleys, and volcanoes enrich soils. These slow movements create the canvas upon which evolution paints. Water, the solvent of life as we know it, arrived through a combination of mechanisms. The primordial Earth likely trapped some water as steam during its formation, but additional supplies came from icy planetesimals and comets that bombarded the early planet. Each collision delivered not just water, but organic molecules synthesized in interstellar space. The combination of an ocean-bearing surface and a stable, moderate climate allowed early chemistry to become biology. The story of water reminds us that habitability is often a product of both local conditions and cosmic delivery. Our star, too, has a life cycle. It was born from a cloud of gas and dust roughly 4.6 billion years ago, igniting hydrogen fusion in its core. Over time, the sun will brighten. In about 1 billion years, Earth's oceans may boil away. In roughly 5 billion years, the sun will swell into a red giant, engulfing Mercury and Venus, and possibly Earth. Afterwards, it will shed its outer layers to form a planetary nebula, leaving behind a white dwarf that will cool for trillions of years. These timescales dwarf human history, yet they serve as a reminder that even seemingly eternal lights have finite lifespans. The architecture of our solar system may have influenced life's prospects. Jupiter's immense gravity acts as a shepherd, deflecting or capturing many comets and asteroids that might otherwise strike the inner planets. Its presence may have reduced the frequency of catastrophic impacts after the tumultuous early period, giving life on Earth a chance to stabilize. At the same time, interactions between the giant planets have reshaped the orbits of smaller bodies, sending objects inward and outward in chaotic dances. Gas giants may be both protectors and perturbators, illustrating the complex roles they play in planetary systems. When we think about the far future, we often confront our impermanence. Civilizations may come and go, continents will drift, and species will evolve or vanish. Yet the atoms that make up our bodies will persist, becoming parts of other organisms, rocks, or even stars. Some imagine that humans, or our descendants, could migrate to other worlds, carrying culture and memory with them. Others contemplate digital minds that inhabit artificial environments. All of these futures rest on our understanding of physics and our capacity for cooperation. They also depend on our willingness to look beyond immediate horizons. On even grander scales, the universe itself evolves. Observations show that galaxies are moving away from each other, that the expansion of space is accelerating due to a mysterious dark energy. If this acceleration continues, galaxies outside our local group will eventually slip beyond the edge of our observable universe. Stars will burn out, leaving white dwarfs and neutron stars. Protons may decay. Black holes will evaporate through quantum processes over unimaginable times. Some theories envision a big rip tearing apart atoms. Others suggest cyclic bounces. Each scenario emphasizes the vastness of cosmic time and the humble span of our own lives. Everything is connected through cycles of creation and destruction. Massive stars forge heavy elements in their cores and in their explosive deaths. Those elements seed new generations of stars and planets, enabling the chemistry of life. Planets themselves experience cycles: ice ages, greenhouse epochs, mass extinctions, and radiations. Even galaxies, undergo mergers and interactions that trigger bursts of star formation. These nested cycles mean that the universe is not static, but dynamic, constantly reshaping itself. Our existence is a brief part of these cycles, yet our actions may influence how some play out locally. In recent decades, astronomers have opened new windows on the cosmos. Neutrino detectors buried deep in Antarctic ice detect ghostly particles from supernovae and the Sun. Gravitational wave observatories like LIGO and Virgo sense ripples in spacetime caused by colliding black holes and neutron stars. These new senses complement traditional observations of light, allowing us to probe phenomena that were once invisible. As instrumentation improves, we may detect neutrino emissions from extraterrestrial technosignatures or gravitational pulses from engineered structures. Expanding our sensory palette deepens our capacity to discover anomalies. The intersection of science and art is also part of this story. When spacecraft carry music, images, and greetings into interstellar space, they blend curiosity with creativity. The Voyager Golden Record, with its medley of whale songs and human laughter, is not just data, but a portrait of Earth's diversity. Artists often respond to scientific discoveries by creating works that evoke cosmic wonder, while scientists draw inspiration from literature and film. This mutual influence reflects a broader truth. Exploring the universe is a cultural endeavor that engages emotions as much as intellect. Different belief systems engage with the possibility of other life in diverse ways. Some religious traditions leave room for multiple worlds populated by spiritual beings. Others focus on Earth as the sole arena of salvation. Discovering extraterrestrial life could challenge or enrich these views. Philosophers and theologians debate whether the existence of other intelligences would alter concepts of uniqueness and purpose. For many, the prospect is a spur to humility, reminding us that our understanding of creation is partial. The conversation around life beyond Earth thus extends beyond science into ethics and meaning. Cosmic weather affects our daily lives. Solar flares and coronal mass ejections hurl streams of charged particles toward Earth, potentially disrupting communications, GPS, and power grids. On larger scales, variations in cosmic ray flux may influence cloud formation and climate, though the mechanisms are still debated. Understanding these effects is crucial as we become more dependent on technology. It also underscores that space is not a benign vacuum, but a dynamic environment. Habitability includes not only stable temperatures, but also resilience to energetic events emanating from the star and beyond. When considering exoplanets, we often think of their moons. Just as Jupiter's moon Europa and Saturn's moon Enceladus may harbour oceans beneath ice shells, exomoons around distant giants could provide habitats. Detecting exomoons is challenging. Their gravitational tugs and dim crossings produce subtle signals, yet efforts are underway to identify such companions. A large moon can stabilize a planet's axial tilt, moderating seasons and climate. Moons may also experience tidal heating, creating internal oceans independent of stellar warmth. The diversity of potential abodes continues to broaden our search. Stories about the stars are woven into the fabric of cultures. Indigenous peoples map clan histories onto constellations, encode calendars in the heliacal rising of bright stars, and convey lessons through sky lore. For them, the cosmos is not an abstract collection of balls of gas, but a living tapestry intertwined with land and community. Listening to these stories reveals alternative ways of relating to the universe, relational rather than exploitative, participatory rather than observational. Incorporating such perspectives enriches the narrative and reminds us that knowledge comes in many forms. Looking outward has practical benefits for looking inward. The realization that Earth is but a pale blue dot floating in space can motivate environmental stewardship. Viewing our planet from afar, as astronauts have reported, instills a sense of fragility and interconnectedness. Awareness of planetary boundaries and the rarity of life in the cosmos can inspire policies that protect habitats, preserve biodiversity, and mitigate climate change. The search for others may help us care better for ourselves, turning cosmic curiosity into terrestrial responsibility. Radiation from space also plays a role in evolution. Cosmic rays, high-energy particles accelerated by supernovae and other events, constantly bombard Earth's atmosphere. They create showers of secondary particles that sometimes penetrate down to the surface. These energetic particles can cause mutations in DNA, contributing to genetic variation. While most mutations are neutral or harmful, a few enable organisms to adapt to new conditions. Thus, cosmic phenomena shape the trajectory of life, not only through catastrophic events, but also through subtle, everyday influences. Speculative ideas about time travel or backward signals occasionally surface in discussions about contact. Some propose that civilizations might send messages encoded in cosmic background radiation or gravitational waves that travel through time differently. Others imagine that advanced beings could manipulate spacetime to send information backward, warning younger civilizations of dangers. While such notions are firmly in the realm of conjecture, they highlight the creative breadth of thought that the search for life inspires. They also remind us to stay open to unexpected channels of communication. At times, the vastness of the universe can feel overwhelming. Our minds struggle to grasp scales of billions of years or trillions of kilometers. Yet within that vastness, patterns repeat. Spiral galaxies echo the shape of seashells. Branching rivers resemble neural networks. Fractals appear in coastlines, snowflakes, and electrical discharges. Recognizing these echoes across scales fosters a sense of coherence. It suggests that complexity emerges from simple rules applied recursively, whether in galaxies or fungi. Appreciating these patterns can deepen our sense of connection with the cosmos. Mathematics is a language that bridges minds. If we ever receive a signal, it might encode prime numbers, ratios, or geometric shapes that represent universality. Our brains are wired to detect patterns, to recognize sequences and symmetries. Mathematics underlies the orbital resonances that keep moons in stable configurations, the chemical bonds that form molecules, and the algorithms that process telescopic data. By honing our mathematical intuition, we prepare ourselves to recognize both natural phenomena and potential messages crafted by other intelligences. Biology teaches us to expect surprises. Viroids are tiny circular strands of RNA that infect plants without coding for proteins. Prions are misfolded proteins that induce other proteins to misfold, causing diseases. Viruses straddle the boundary between life and non-life. Incapable of reproduction, without hosts, yet capable of evolution. Extremophiles thrive in boiling acid, under immense pressures, and within nuclear reactors. These examples broaden our definitions of life and resilience. They caution us against narrow assumptions when searching for alien biology, and encourage us to design experiments that detect unfamiliar kinds of organization. Communication across species is inherently challenging. On Earth, we struggle to interpret the songs of whales or the dances of bees. Language shapes and constrains thought, and different cognitive architectures yield different modes of expression. An alien signal might be encoded in electromagnetic pulses that use a syntax foreign to us. It could be as terse as a beacon or as layered as poetry. Preparing to understand such a message involves studying information theory, linguistics, cognitive science, and music. It also entails humility, recognizing that translation is as much an art as a science. Imagining possible technosignatures pushes our creativity. Beyond radio transmissions and megastructures, we might look for waste heat from computational substrates, unnatural chemical combinations in atmospheres, or irregularities in stellar pulsations. We may search for laser emissions, neutrino beams, or gravitational lensing used as telescopes. The challenge is to distinguish deliberate artifacts from natural anomalies. This requires deep knowledge of astrophysics and open-mindedness. Each proposed signature invites targeted observations and helps refine the Drake equation's factor related to communicative behavior. Our capacity for wonder has been a constant. Across cultures and ages, people have stood under the same sky and felt awe. This emotion drives us to ask questions, to build tools, to share stories. It is a source of motivation and resilience. When setbacks occur, when funding is cut, or instruments fail, wonder keeps us going. It reminds us that knowledge is worth pursuing for its own sake, and that the unknown is not frightening, but alluring. Cultivating wonder in education ensures that future generations will continue the search. The narrative will continue beyond this point. Ahead lies an exploration of how emerging technologies may transform our estimates, how deeper philosophical debates may influence our approach, and how new discoveries could challenge or confirm our assumptions. There will be further discussions of the roles of viruses, of the ethics of synthetic biology, of the anthropic principle, of cosmic inflation, of multiverse theories, and of the possibility that we inhabit a simulation. The journey is far from over. We end here not because we have exhausted the topic, but because pauses are necessary. They allow reflection, integration, and anticipation. The night sky has long been a canvas for human imagination. Imagine standing beneath a dome of stars, sensing the gentle curve of the earth as it slips into shadow, and hearing nothing but your own breathing and the hum of insects. People have asked for millennia whether those points of light hold other worlds with eyes looking back. Ancient philosophers in Greece and India debated the plurality of worlds, and poets in ancient China wondered whether the moon was mirrored by another moon in a far-off realm. These early questions were whispers, unanswerable curiosities that folded into myths and folk tales. As centuries passed, our questions sharpened. Telescopes revealed that the stars were suns in their own right, scattered through a vast galaxy rather than pasted on a crystalline sphere. With each discovery, from Galileo's moons to Herschel's nebulae, our sense of scale expanded, and the odds of solitude seemed to shrink. The Enlightenment brought a flowering of speculation. Philosophers like Fontenelle spoke of inhabited worlds in his popular dialogues, and scientists like Huygens imagined creatures under alien suns. The Industrial Revolution added steam and electricity to our lives, but could not quell the older, quieter dreams of company in the cosmos. When Sputnik's beep crossed oceans in 1957, it marked not just a geopolitical milestone, but a turning point in our relationship with space. Suddenly, the void was not an abstract idea, but a reachable frontier. Radio astronomy matured, and science fiction spilled over into real engineering. Within this ferment, a young astronomer named Frank Drake swept the radio dial in 1960, pointing an antenna at nearby stars and listening for signals. His experiment, called Project Ozma, was a first attempt to eavesdrop on another civilization. Although he heard nothing but cosmic hiss, the act itself crystallized the desire to quantify our ignorance. The following year, Drake organized a small meeting at the Green Bank Observatory in West Virginia. Gathered in that wood-paneled room were a handful of scientists, each of whom had turned their curiosity toward the possibility of life beyond Earth. To guide their discussion, Drake wrote a string of symbols on a blackboard. Each term represented a question. How many stars are born in the galaxy each year? What fraction of those stars host planets? How many of those planets might be suitable for life? What fraction actually spawn life? How many of those life-bearing worlds produce intelligent beings? And how many of those civilizations choose to communicate? Finally, how long do such communicating civilizations last? The product of those factors, Drake suggested, would give an estimate of the number of civilizations in the Milky Way whose signals might be detectable at this very moment. It was a heuristic, not a precise calculation, but it allowed a structured conversation. Participants could plug in optimistic or pessimistic values and see how assumptions cascaded. In that humble setting, the Drake equation was born not as a prediction, but as a way to organize bewildering unknowns. It has since become a symbol of scientific humility, a reminder that even careful mathematics can only scaffold our wonder when data are sparse. At first glance, the equation looks like something from a physics exam, but each variable is freighted with biology, geology, and sociology. The rate of star birth hints at swirling clouds condensing into shining furnaces. The fraction of stars with planets reflects planet formation theories confirmed by exoplanet surveys. The number of habitable planets per system depends on orbital dynamics, planet size, and the sweet spot where liquid water can persist. The fraction of planets where life arises invites chemistry, random luck, and perhaps inevitable processes. The next fraction, representing worlds that develop intelligence, touches on evolution and cognition. Then comes the fraction that chooses to communicate, an assumption about curiosity and technology. Finally, the longevity term speaks to sustainability, resilience, and the hazards of cosmic and self-inflicted cataclysm. Before wrestling with the variables, we must ask a deeper question. What do we mean by life? NASA has offered a working definition: a self-sustaining chemical system capable of Darwinian evolution. Terran life relies on carbon's versatile bonding, uses water as a solvent, and depends on elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. It harnesses free energy, builds structures, grows, reproduces, and responds to its environment. Through billions of years, it has diversified into microbes, plants, animals, and fungi, all sharing the language of DNA and the machinery of cells. This common heritage makes biologists confident that life on Earth is a single lineage. But does life elsewhere have to be built the same way? Astrobiologists debate whether life could use different chemistries. Maybe silicon forms complex backbones in exotic solvents, or ammonia plays the role of water under colder conditions. Some argue that carbon's flexibility and water's polarity make them uniquely suited, but others caution against Earth-centric thinking. If we restrict our search to our own ingredients, we might miss thriving ecosystems with unfamiliar metabolisms. To detect life, we look for biosignatures, measurable patterns or compounds that hint at biological activity. These include isotope ratios, characteristic of biological processes, molecules like oxygen or methane that coexist in disequilibrium, and complex organic compounds. For a biosignature to be reliable, it must be produced by life, survive in the environment, and be detectable from afar. Definitions of life also intersect with definitions of intelligence. Intelligence is not merely problem-solving. It encompasses abstract reasoning, language, tool use, and social complexity. Many species on Earth exhibit elements of intelligence. Corvids fashion hooks from twigs, octopuses open jars, and dolphins learn elaborate vocalizations. Yet only humans have developed symbolic language and the ability to build technologies that can signal across interstellar distances. Whether such a leap is inevitable on life-bearing planets is unknown. Earth took billions of years to produce hominins, and intelligence may be contingent on quirks of environment and evolution, rather than an evolutionary destiny. Our home galaxy provides the setting for this equation. The Milky Way is a barred spiral, tens of thousands of light-years across, with a central bulge, a thin disk of stars, gas and dust, and a sparse halo of ancient stars and dark matter. The Sun orbits in the disk about 8 kiloparsecs from the center. Metallicities, which measure the abundance of elements heavier than helium, vary across the galaxy. They are higher in the inner disk and lower in the halo. This matters because metals are the building blocks of rocky planets. Regions with too few metals may struggle to produce Earth-like worlds, while regions too close to the galactic center may be bathed in radiation from frequent supernovae and the central black hole. Astrobiologists therefore speak of a galactic habitable zone, an annulus, where conditions may be favorable for life, though its boundaries are fuzzy and stars migrate over time. The history of the galaxy is entwined with the history of star formation. Observations show that the universe as a whole experienced a peak in star formation around 3.5 billion years after the Big Bang, during a period dubbed cosmic noon. The rate then declined over the next 10 billion years as galaxies exhausted their cold gas and feedback from stars and black holes heated or expelled the remaining supply. In the Milky Way today, about 1 to 2 solar masses worth of gas condenses into new stars each year. Because most stars formed are red dwarfs with masses less than that of the Sun, this translates to roughly 6 to 7 new stars annually. 10 billion years ago, when the galaxy was younger and gas more abundant, star formation was perhaps 10 times higher. These temporal variations affect the number of potential cradle worlds available at different epochs. Time also enters the equation through the longevity term. If a communicating civilization lasts only a few hundred years, as ours has so far, the chances of overlap between civilizations shrink dramatically. But if civilizations endure for hundreds of thousands or millions of years, then even if they are rare, the galaxy could be humming with voices. The term encapsulates not just natural hazards like asteroid impacts, supernovae, and gamma-ray bursts, but also internal threats: climate change, resource depletion, warfare, and technologies that outpace wisdom. It prompts us to reflect on our own trajectory and whether we can become a long-lived, stable presence in the cosmos. As we wade through these questions, we must remember the uncertainties. Each parameter in the Drake equation has a range rather than a single value. Surveys of star formation rates rely on counting young stars, modeling gas consumption, or measuring radiation from newborn clusters. Estimates of the fraction of stars with planets have improved dramatically thanks to missions like Kepler and various micro-lensing surveys. Yet small planets far from their stars remain challenging to detect. Determining the number of habitable planets depends on models of climate, geology, and magnetism. The fractions describing the emergence of life, intelligence, and communication are essentially unknown, derived from a sample size of 1. And longevity remains a philosophical rather than empirical parameter. Rather than viewing the equation as a calculation to be solved, many scientists treat it as a conversation starter. Astronomer Jill Tarter, one of the pioneers of SETI, has called it a wonderful way to organize our ignorance. By breaking the problem into parts, we can attach data and theories where possible and clarify what we do not know. It also highlights where new observations, like exoplanet discoveries, studies of extremophiles, or surveys of technosignatures, can narrow uncertainties. Perhaps most importantly, it reminds us that the search for life is not just a scientific endeavor, but a reflective one. In pondering others, we are forced to examine ourselves. Our story thus far has traced the lineage of a question from ancient musings through a chalkboard equation. We have outlined the variables that connect cosmic physics, planetary science, biology, and sociology. We have recognized the importance of defining life and intelligence, sketched the structure of our galaxy, and touched upon cosmic history. We have acknowledged the profound uncertainties that accompany each step. Now we are poised to dive deeper into each term of the equation, to unpack the science behind the variables, and to appreciate the subtleties hidden within the simple product. The next chapters will slow down and explore the birth of stars, the prevalence of planets, the conditions for habitability, the chemistry that sparks life, the emergence of minds, the urge to communicate, and the endurance of civilizations. Our journey continues gently into the heart of the equation. To count how many communicative civilizations might exist, we begin with the number of stars. Stars are born in dense molecular clouds, where turbulence and gravity conspire to compress gas into clumps. When a clump accumulates enough mass, it collapses under its own weight and heats up until nuclear fusion ignites. The star then shines, balancing gravity's inward pull with the outward pressure of fusion. The rate at which this process occurs across the galaxy is not constant. Today, the Milky Way forms about 1 to 2 solar masses of stars per year, resulting in several new stars annually. Earlier in cosmic history, when the galaxy was richer in cold gas, the rate was much higher. This historical context matters because older stars could host planets and life that had billions of years to evolve before our sun was born. Star formation is not uniformly distributed. Spiral arms trace regions where gas density is higher, promoting bursts of star birth. The central bar channels gas inward, and the halo contains ancient stars formed in the galaxy's youth. The types of stars produced also vary. Most newly formed stars are red dwarfs, cooler and dimmer than the sun. They burn their fuel slowly and can live for trillions of years, providing long, stable conditions for potential planets. More massive stars live fast and die young, exploding as supernovae that enrich the interstellar medium with heavy elements. These explosions seed future generations of stars and planets with the ingredients for life, but also bathe nearby systems in radiation that can strip atmospheres. Thus, the distribution and longevity of stars influences the number and quality of potential habitats. Our next parameter, the fraction of stars with planets, has undergone a revolution. For centuries, planets around other stars were speculative. In the 1990s, the first exoplanets were confirmed. Gas giants orbiting close to their stars, surprising astronomers and challenging theories. Space missions like Kepler revealed thousands of planets using the transit method, which measures dips in starlight as planets pass in front of their hosts. Microlensing surveys added planets farther from their stars by observing how foreground stars and planets magnify background starlight. Radial velocity measurements tracked tiny wobbles in a star's motion caused by orbiting planets. These techniques together have shown that planets are the rule, not the exception. Microlensing studies suggest that roughly half of stars host Neptune-mass planets, and a similar or greater fraction host smaller super-Earths. Jupiter-mass planets are less common, but even they occur around about 1 in 6 stars. In other words, most stars likely have families of worlds. Planets come in myriad forms. Some are hot Jupiters, skimming their stars' surfaces. Others are frigid giants in distant orbits. There are rocky terrestrial planets, water worlds, and hybrid types we cannot yet imagine. Planet formation appears to be a natural byproduct of star formation. As a star forms, a rotating disk of gas and dust surrounds it. Within this disk, particles collide and stick, growing into planetesimals and eventually planets. The architecture of a system depends on the disk's mass, composition, and dynamics. Our own solar system, with its orderly orbits and mix of rocky and gas giant planets, is just one arrangement among countless possibilities. This diversity means that when we talk about the fraction of stars with planets, we must also consider the fraction with planets in the habitable zone, the region around a star where liquid water can exist on a planet's surface. The habitable zone, often called the Goldilocks zone, is not a simple ring. Its boundaries depend on a star's luminosity, the planet's atmosphere and greenhouse gases, cloud cover, surface reflectivity, and geological cycles, like the carbonate-silicate cycle that regulates carbon dioxide. For a star like the Sun, the classical habitable zone extends roughly from the orbit of Venus to that of Mars. Around dimmer red dwarfs, the zone is much closer in, so planets receive similar energy despite orbiting only a fraction of an astronomical unit away. However, proximity brings challenges. Tidal locking can freeze one hemisphere and scorch the other, and stellar flares from red dwarfs can erode atmospheres. Around more massive stars, the habitable zone lies farther out, but may be short-lived because such stars burn out quickly. Calculating the number of habitable worlds thus requires understanding stellar types, planetary atmospheres, and orbital dynamics. Even within the habitable zone, life must contend with planetary characteristics. A planet must be massive enough to retain an atmosphere, but not so massive that it becomes a gas giant. It needs an internal heat source to drive plate tectonics, which recycles nutrients and regulates climate through volcanism and seafloor spreading. A magnetic field can shield the surface from stellar wind and cosmic rays. The presence of a large moon can stabilize the planet's axial tilt, moderating seasons. Giant planets in the outer system may play the role of guardians, deflecting comets and asteroids that could sterilize the inner worlds. These factors, often called rare Earth considerations, have led some to argue that truly habitable planets may be uncommon. Others counter that life is resilient and might adapt to a wide range of conditions. The truth likely lies between these extremes. Now we come to the fraction of habitable planets where life actually emerges. On Earth, life appears to have arisen relatively quickly once conditions permitted. Evidence of microbial mats and stromatolites suggests that by 3.5 billion years ago, life was flourishing in shallow seas. The origin of life, or abiogenesis, is still not fully understood. It probably involved the formation of simple organic molecules from simpler precursors, the assembly of self-replicating RNA or related polymers, and the encapsulation of these molecules within membranes. Energy gradients, such as those found near hydrothermal vents, could have powered early metabolism. Whether such processes are likely or rare is unknown. Some argue that given the right chemistry and energy, life is almost inevitable. Others posit that the emergence of self-replicating molecules is so improbable that Earth might be unique within a vast volume. Once life appears, the next critical transition is the evolution of complexity and intelligence. For billions of years, life on Earth remained microbial. Only around 600 million years ago did multicellular organisms flourish in the oceans during the Cambrian explosion. This surge of diversification produced a wide array of body plans and eventually led to vertebrates, insects, and plants. The emergence of intelligence capable of creating technology occurred only within the last few million years, and only in one lineage of primates. Some scientists note that although structures like eyes have evolved multiple times independently, brain power akin to ours has not. This suggests that intelligence may not be a convergent feature of evolution. However, the fossil record is but one example. Life elsewhere may explore different evolutionary paths, and intelligence might arise under different pressures. Even if intelligence evolves, it need not lead to technology. Dolphins and elephants display complex social behaviors and communication, but have not built radio telescopes. Intelligence might be used for survival and social negotiation rather than tool-making. Cultural and environmental factors influence whether a species develops agriculture, writing, metallurgy, and eventually electronics. Our own technological trajectory was shaped by ice ages, continental drift, resource distribution, and cultural exchange. It might be that many worlds host intelligent beings who live in harmony with their environments without emitting radio waves or lasers that could betray their presence. The fraction of intelligent species that choose to communicate deliberately with unknown others may be small, or their methods may differ from ours in ways we have not anticipated. Communication itself is multifaceted. Early humans sent smoke signals and carved markings on bone. Today, we broadcast television and internet signals that leak into space, though such leakage becomes harder to detect with digital compression and fiber optics. Purposeful transmissions, like the Arecibo message sent in 1974 or the Voyager Golden Records, are rare and symbolic. A truly communicative civilization might build beacons, modulate pulsars, or harness gravitational waves. Alternatively, advanced species might move beyond electromagnetic communication, creating networks of quantum entanglement or other physics we have yet to discover. Our search methods are limited by our own understanding and by the technology we possess. Recognizing a signal also requires distinguishing it from the cacophony of natural astrophysical phenomena. The final parameter, the longevity of communicating civilizations, acts like a window that determines overlap in cosmic time. If civilizations transmit for millions of years, then even if they arise infrequently, multiple such civilizations could coexist and detect each other. If they flash like fireflies for mere centuries, they might never overlap. Longevity is influenced by internal dynamics, resource management, social cohesion, ethical development, and by external events like asteroid impacts, stellar flares, or supernovae. Some forms of technological progression may inherently risk self-destruction through weapons, bioengineering, or artificial intelligence. Others might allow for sustainable equilibrium. In this context, thinking about longevity becomes both an astronomical and a moral inquiry, encouraging us to ponder how to extend our own communicative lifespan. Beyond the numbers, the Drake equation raises philosophical dilemmas epitomized by the Fermi paradox. If the universe is so vast and the ingredients for life appear common, where is everybody? Enrico Fermi posed the question over lunch in the 1950s, and it has haunted discussions ever since. One proposed resolution is the Great Filter, the idea that there is a stage in the progression from chemistry to cosmic colonization that is exceptionally hard to cross. This filter could lie behind us, in which case life or intelligence is rare or ahead of us, meaning that advanced civilizations regularly self-destruct or otherwise fail to spread. Some analyses break the journey into multiple bottlenecks: the formation of suitable planetary systems, the emergence of replicating molecules, the leap to eukaryotic cells, the evolution of multicellularity, the appearance of tool-using intelligence, the development of technology, and the capacity for interstellar expansion. Each stage may present improbable hurdles, and the exact placement of the filter remains a matter of debate. Despite the silence, searches continue. Since Project Ozma, numerous SETI initiatives have scanned the skies. Radio telescopes like the Green Bank Telescope, Parkes Observatory, and the Allen Telescope Array have listened for narrowband signals that would stand out against natural radio emissions. Optical SETI looks for brief flashes of laser light. Breakthrough, Listen, funded by private philanthropy, surveys millions of stars across wide frequency bands. Some efforts exploit piggyback observations, analyzing data collected for other astronomical purposes. While no confirmed signals have been detected, the range of frequencies and sky coverage explored so far is a tiny fraction of the possible parameter space. To borrow an analogy, searching for radio beacons in the galaxy is like scooping a cup of water from the ocean and declaring there are no fish. SETI is complemented by the search for biosignatures and technosignatures. Telescopes, such as the Hubble Space Telescope, James Webb Space Telescope, and upcoming missions like the Roman Space Telescope, can analyze the spectra of exoplanet atmospheres as planets transit their stars. They look for combinations of gases like oxygen, methane, and carbon dioxide that are hard to maintain simultaneously without biological replenishment. Seasonal variations, unusual albedo patterns, or high levels of certain compounds may hint at life. Technosignatures include phenomena that are unlikely to arise from natural processes. Narrowband radio transmissions, periodic flashes, structures obscuring starlight, excessive infrared radiation from waste heat, or chemical pollutants in atmospheres. Each potential signature requires careful consideration to avoid false positives. A pulsar, for example, was initially dubbed a little green man signal, but quickly understood as a rotating neutron star. Looking closer to home, our own solar system hosts several worlds that might harbour life. Mars preserves evidence of ancient riverbeds and lakes, and may contain subsurface aquifers today. Europa and Enceladus, moons of Jupiter and Saturn, are encased in ice, but possess internal oceans heated by tidal flexing. Plumes from Enceladus contain water vapor and organic molecules. Titan has lakes of liquid methane and ethane on its surface, and a thick nitrogen atmosphere with complex chemistry. Ganymede and Callisto may hold buried seas. Exploring these worlds requires robots that can drill through ice or analyze plume material, missions that are planned and may soon broaden the search for life from planetary atmospheres to subsurface oceans. Beyond the question of life, contemplating other civilizations invites speculation about culture, ethics, and communication. Would alien societies think like us? Would they experience curiosity, art, and music? Evolutionary pressures might favor cooperative social structures, but the specifics of culture could be wildly diverse. Communication could involve senses we do not possess, or languages encoded in mediums we do not use. Misinterpretation is a risk even among human cultures. cross-species comprehension is exponentially harder. Some scientists propose that mathematics, particularly prime numbers or geometric patterns, offers a universal language. Others suggest that shared experiences, like the periodic table or the structure of the hydrogen atom, might serve as starting points for interstellar conversation. As technology advances, our own signals are changing. Early radio and television broadcasts were powerful and omnidirectional, but modern communication relies more on fiber optics, spread spectrum signals, and encryption. Leakage into space is diminishing, making our planet less conspicuous to eavesdroppers. Deliberate transmissions continue to be discussed, with debates about whether broadcasting our presence is wise. Some argue that any civilization capable of harming us would already know we are here from our atmospheric signatures. Others caution against attracting attention in a cosmos whose moral landscape is unknown. These debates remind us that the Drake equation is not merely theoretical, but implicates real choices about our collective future. Advances in technology also feed back into the equation itself. As we discover more exoplanets, we refine estimates of the fraction of stars with planets and the distribution of planet sizes and orbits. Observations suggest that small, rocky planets are abundant. Studies of the Milky Way's metallicity gradient inform models of where such planets might form. Laboratory experiments and computational chemistry explore the plausibility of alternative biochemistries, widening our view of what counts as a habitable environment. Synthetic biology experiments show how life's building blocks can be assembled from simpler compounds. In addition, we are beginning to detect exocomets, exomoons, and debris disks, painting a richer picture of planetary systems. Each piece of data chips away at the uncertainties in the equation. Meanwhile, discussions of civilization longevity intersect with fields like sustainability, climate science, and geopolitics. Some researchers model scenarios in which civilizations decouple their growth from resource consumption, achieving stable or cyclical states that could persist over geological times. Others explore the likelihood of self-induced collapse through ecological overshoot or technological mishap. The concept of a great filter warns that certain stages of technological development may be treacherous. If nuclear weapons, climate change, or artificial intelligence pose existential risks, then surviving past them may be rare. On the other hand, if humanity navigates these challenges successfully, we might become an example of a long-lived civilization that helps tilt the equation toward higher values of L. The Drake equation has inspired derivatives and extensions. Some versions incorporate spatial and temporal distributions, integrating star formation history and galactic metallicity gradients to estimate how the number of civilizations varies across space and time. Others break down certain factors further, separating the emergence of life into prebiotic chemistry, biogenesis, and the evolution of complex multicellularity. Probabilistic approaches replace single values with distributions, allowing Monte Carlo simulations to generate ensemble predictions. Bayesian frameworks incorporate prior beliefs and update them with new data. These refinements demonstrate that while the original equation was simple, its spirit persists as we build more nuanced models. Despite decades of research, the question remains open. Estimates range from pessimistic solutions, suggesting we may be alone, to optimistic scenarios where thousands of civilizations share our galaxy. The lack of evidence either way keeps the debate alive. Some scientists argue that given the vastness of time and space, our search has barely begun, and we should not be surprised by the silence. Others take the silence as evidence that advanced civilizations are extremely rare or short-lived. Philosophers and sociologists weigh in, discussing the anthropic principle, observer selection effects, and our psychological response to cosmic solitude. The interplay of empirical science and existential reflection makes the topic uniquely compelling. Whatever the actual number of communicative civilizations, the act of asking shapes our understanding of ourselves. It forces us to articulate what we value in life and civilization, to define intelligence and communication, and to confront our vulnerabilities. It invites us to preserve our world, not just for its own sake, but as a participant in a potential community of minds. It also offers a humbling perspective. The universe is vast and indifferent, yet we are capable of pondering our place within it. This perspective can foster both awe and responsibility. As we reach the end of our exploration, we circle back to the gentle question posed at the start. Who else is out there? The Drake equation does not answer it, but provides a compass. By filling in its terms with the best data and theories we have, by discussing uncertainties and possibilities, we engage in a kind of cosmic meditation. We listen to the whispers of radio static, analyze faint starlight, and send out our own messages, all while nurturing the fragile biosphere that made this questioning possible. The search may continue for generations, and that search itself becomes part of the story of any civilization that endures long enough to wonder. In the quiet hours, under a sky spangled with stars, when the Milky Way arches overhead like a luminous river, the mystery feels both intimate and infinite. Each star is a sun. Each sun may have worlds. On some of those worlds, perhaps creatures watch their own sky and ask the same questions. Whether the answer is that we are gloriously alone or part of a hidden chorus of minds, the act of wondering binds us to the cosmos. With patience and care, we continue listening, imagining, and exploring, guided by curiosity and grounded in science. Our story is a thread woven into the fabric of the universe, and by seeking others, we come to know our own thread more deeply. Stars do not form in isolation. They are born in nurseries, shrouded in dust and gas. In these stellar wombs, turbulence and magnetic fields shape the filaments that eventually collapse into stars. Astronomers peer into these cold, dark regions with infrared and radio telescopes, tracing the glow of warm dust and molecules like carbon monoxide. Observations reveal protostellar jets carving cavities, disks swirling around infant stars, and clusters emerging together. Some of these clusters remain bound as open clusters or globular clusters. Others disperse, releasing their stars into the galactic field. The distribution of such nurseries is uneven, concentrated in spiral arms where density waves compress the gas. As the galaxy ages, feedback from previous generations, supernova shockwaves, and stellar winds both trigger and hinder new star formation. The earliest stars in the universe, known as population 3 stars, were fundamentally different from those around today. Composed almost entirely of hydrogen and helium, they lacked the heavy elements that help cool collapsing gas clouds. As a result, they were likely massive and short-lived, exploding as hypernovae that forged the first metals. Their deaths seeded the interstellar medium with carbon, oxygen, and other elements necessary for planets and life. Over cosmic time, successive generations, called population 2 and population 1 stars, incorporated more heavy elements. Our Sun is a relatively late arrival, formed from enriched gas some 9 billion years after the Big Bang. The rise and fall of star formation across cosmic history reflects this evolving chemical landscape, the assembly of galaxies, and the dance of dark matter and baryons. When astronomers describe the star formation rate today as 1 to 2 solar masses per year, it is an average across a galaxy, that spans 100,000 light-years. Local regions can experience brief bursts or long lulls. Dwarf galaxies undergoing interactions may ignite starbursts, temporarily elevating their rates. Massive galaxies with active nuclei may suppress star formation as jets from central black holes heat the gas. On grander scales, the cosmic web feeds gas into galaxies along filaments, sustaining star formation. If we aim to estimate the number of potential habitats, we must factor in not only the current rate, but also the integrated history. Because planets formed billions of years ago, have had time for life and intelligence to evolve. Modern surveys of exoplanets illustrate the power of different detection techniques. The transit method, famously employed by the Kepler mission, monitors the brightness of stars for tiny dips when planets pass in front. This technique is sensitive to the size of the planet and the inclination of its orbit. It favors large planets close to their stars. Radial velocity measures the wobble of a star due to the gravitational tug of an orbiting planet by detecting shifts in spectral lines. Direct imaging blocks the star's light to capture faint glimmers of orbiting companions, typically massive young planets far from their stars. Gravitational microlensing leverages the gravitational field of a star and its planets to magnify background starlight. Each method samples different regions of parameter space, and together they build a census of planetary diversity. Notable exoplanets capture the imagination. There is 51 Pegasi b, the first hot Jupiter discovered around a sun-like star, orbiting its host in just 4 days. There is Kepler 452b, a super-Earth in the habitable zone of a sun-like star, sometimes called Earth's cousin. TRAPPIST. One hosts 7 Earth-sized planets, several in the habitable zone, orbiting a cool dwarf star. Some exoplanets have eccentric orbits, scorching summers and frigid winters. Others are tidally locked, with permanent day and night sides. There are worlds with iron rain, glass storms, and lava oceans. Each new discovery broadens our view of what is possible and underscores the need to refine our criteria for habitability. The concept of habitability itself has expanded in recent years. Beyond the classical habitable zone, scientists consider subsurface oceans on icy moons, where tidal heating creates pockets of liquid water. They explore the idea of atmospheres thick enough to support a greenhouse effect, even far from a star, turning rogue planets into potential havens. They investigate the role of plate tectonics, which recycles carbon dioxide and stabilizes climate over geological timescales. They ponder worlds around red dwarfs, where frequent flares might strip atmospheres, and ask whether thick atmospheres or magnetic fields could provide protection. They discuss the continuous habitable zone, the region around a star that remains habitable over billions of years as the star brightens. These nuances remind us that the number of habitable planets is not a fixed fraction, but depends on a web of interrelated factors. Extremophiles on Earth demonstrate that life can adapt to conditions once deemed hostile. Microbes thrive in boiling acid pools, deep-sea hydrothermal vents, polar ice, radioactive waste, and rocks deep within the crust. They metabolize sulfur, iron, arsenic, and even radiolysis products. Some survive desiccation, high radiation doses, and the vacuum of space. These organisms expand our sense of what habitable means and inspire models of life on Mars, Europa, and exoplanets. Studies of ancient bacteria revived from salt crystals or permafrost suggest that life can persist over millions of years in dormant states. Such resilience implies that life, once established, could endure long periods of environmental stress, making the fraction of planets where life persists potentially higher than naive estimates. The origin of life remains a central mystery. Laboratory experiments simulate early Earth conditions, producing amino acids and nucleotides from simple gases and energy sources like lightning or ultraviolet light. Other experiments test the RNA world hypothesis, in which RNA molecules act as both genetic material and catalysts. Researchers explore hydrothermal vent environments where mineral surfaces could catalyze the assembly of organic molecules. Some hypotheses involve lipid vesicles spontaneously forming protocells. Alternative ideas invoke panspermia, the transfer of life's building blocks, or even life itself between planets via meteorites. Meteorites have been found to contain organic compounds, and impact experiments show that microbes can survive the shock of launch and re-entry. If life can spread between worlds, then the Drake equation's term for the emergence of life might be less about independent genesis and more about transfer mechanisms. Evolutionary history on Earth is punctuated by mass extinctions and recoveries. The end Ordovician, late Devonian, end Permian, end Triassic, and end Cretaceous extinctions wiped out large percentages of species, resetting ecosystems. After each catastrophe, life rebounded, often diversifying in new directions. The Permian extinction paved the way for dinosaurs. The Cretaceous extinction allowed mammals to proliferate. Intelligence emerged during a comparatively stable period in Earth's climate, but had events unfolded differently, if a different asteroid had struck, or if volcanic activity had persisted, our species might not exist. These contingencies suggest that intelligence is sensitive to planetary history. On other worlds, different catastrophes could either hinder or accelerate the emergence of advanced life. Social evolution further complicates the journey to technology. Homo sapiens lived as hunter-gatherers for hundreds of thousands of years before agriculture. The development of farming led to surplus food, specialized professions, and eventually cities and writing. Trade networks spread innovations. Competition and cooperation drove technological leaps. The Industrial Revolution and scientific method accelerated progress, culminating in the ability to send signals into space. Other civilizations might follow wholly different trajectories. They might remain nomadic, developing oral traditions without written records, or they might achieve sustainable technologies that leave minimal ecological footprints. The assumption that intelligence inevitably leads to radio communication may be parochial. Nevertheless, certain physical constraints apply. Electromagnetic waves are a natural choice for interstellar communication because they travel at light speed and can be modulated to carry information. The radio window, spanning frequencies where Earth's atmosphere is transparent, is attractive to both senders and receivers. The hydrogen line at 1420 MHz and the hydroxyl line at 1612 MHz form a quiet region of the spectrum called the waterhole, often suggested as a meeting place for interstellar communication. Civilizations might also use optical frequencies, sending pulses of laser light that could be detected as nanosecond flashes. The challenge is deciding which frequencies to monitor and for how long. Searching the entire sky across all frequencies continuously is currently impossible. Strategies must balance breadth, depth, and duration. In addition to purposeful signals, civilizations might build large structures that betray their presence. Dyson spheres or swarms, arrays of solar collectors around a star, would re-radiate energy in the infrared, altering the star's spectral signature. A civilization mining asteroids on a grand scale might create unusual dust patterns. Artificial illumination on the night side of an exoplanet could be detectable in reflected light. Pollutants like chlorofluorocarbons in an exoplanet's atmosphere, which have no known natural sources, would indicate industrial activity. Detecting such technosignatures requires sensitive instruments and careful interpretation. distinguishing them from natural phenomena like dust clouds, circumstellar disks, or volcanic gases. The Fermi paradox has inspired numerous hypotheses beyond the Great Filter. The zoo hypothesis suggests that advanced civilizations deliberately avoid contact, observing us as we observe animals in a reserve. The dark forest theory posits that civilizations remain silent to avoid attracting predators in a potentially hostile universe. The self-destruction scenario warns that technological species often annihilate themselves before spreading. The resource scarcity hypothesis argues that interstellar travel is so expensive that few attempt it. Some propose that advanced beings retreat into virtual realities, losing interest in physical expansion. Others consider that we are simply early, and that intelligent life has yet to arise in many places. There are also more esoteric ideas, that we live in a simulation, that the universe is teeming with life we cannot recognize, or that there are filtering mechanisms we have not imagined. Anthropic reasoning enters the discussion when we consider that observers must find themselves in environments compatible with their existence. We should not be surprised to inhabit a planet with just the right properties, because if it were otherwise, we would not be here to ponder. Similarly, we might expect to live before a universe becomes crowded with grabby civilizations if their expansion prevents latecomers from having cosmic real estate. These arguments can be slippery, but they remind us to be cautious about drawing conclusions from our singular perspective. Our existence does not guarantee that intelligence is common. It simply indicates that at least one pathway to intelligence exists in the universe. Search strategies are evolving alongside technology. Early SETI projects targeted a handful of nearby sun-like stars. Contemporary surveys examine millions of stars across large swaths of the sky. New instruments like the Square Kilometre Array, SKA, will have unparalleled sensitivity to faint radio emissions. Optical SETI programs monitor stars for laser pulses, while infrared searches look for waste heat signatures. Machine learning algorithms sift through vast datasets to identify unusual signals. Citizen science projects engage the public in analyzing data, tapping into collective curiosity. International collaborations coordinate observations, share data, and develop standard protocols for verifying and responding to possible detections. The detection of phosphine in the atmosphere of Venus in 2020 sparked debate about biosignatures. Some researchers initially claimed the presence of phosphine, a gas associated with anaerobic life on Earth, in Venus's clouds. Subsequent analyses questioned the finding, attributing it to sulfur dioxide or instrumental artifacts. The episode highlighted the challenge of interpreting spectral signatures and the need for multiple lines of evidence. It also reminded us that life could exist in unexpected places, prompting renewed interest in sending probes to Venus's atmosphere. Similarly, observations of methane on Mars and in the plumes of Enceladus raise questions about biological versus geological sources. Resolving these ambiguities requires in situ measurements, laboratory experiments, and robust modeling. Planned missions will expand the hunt for life. NASA's Europa Clipper will fly repeatedly past Europa, mapping its surface and probing its subsurface ocean with ice-penetrating radar and magnetometers. The Enceladus Orbilander concept proposes orbiting Saturn's moon and landing to analyze plume material. The Dragonfly mission will send a rotorcraft to Titan, exploring its dunes and organic chemistry. Mars Sample Return will bring back cores drilled by the Perseverance rover, allowing laboratory analyses for biosignatures. Beyond our system, space telescopes like the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and future large UV/optical IR telescopes aim to characterize exoplanet atmospheres with increasing precision. Each mission may reduce uncertainties in the Drake equation by providing data on habitable environments and potential biosignatures. These explorations are complemented by theoretical advances. Astrobiologists develop models of planetary climate and chemistry under various stellar types. They simulate how clouds affect the reflectivity of exoplanets, how tidally locked worlds circulate heat, and how biogeochemical cycles operate on planets with different compositions. Chemists explore reaction pathways for prebiotic molecules in solvents like methane or supercritical carbon dioxide. Evolutionary theorists examine the conditions under which multicellularity and intelligence evolve, using comparative data from Earth's organisms. Sociologists and political scientists explore scenarios of global cooperation or conflict in the face of existential threats. Each discipline enriches the broader narrative about life and intelligence in the universe. The implications of contacting, or being contacted by, an extraterrestrial civilization are profound. Protocols exist for how to handle a detection, confirm independently, share data openly, and consult the international community before responding. The International Academy of Astronautics has guidelines for dealing with potential signals. Some scientists advocate sending messages proactively, arguing that interstellar communication could foster goodwill and knowledge exchange. Others fear unknown risks. Cultural impacts would vary across societies, potentially challenging religious beliefs, philosophical frameworks, and social cohesion. Literature and cinema have explored these themes, from peaceful exchanges to catastrophic invasions. While fiction dramatizes, it also helps us rehearse our reactions and values. In contemplating the longevity of civilizations, researchers study the lifespan of planetary environments. Earth has remained habitable for billions of years, thanks in part to the carbonate-silicate cycle and plate tectonics. However, the sun will gradually brighten, and in about 1 billion years, Earth's oceans could evaporate. Red dwarf stars, by contrast, remain stable much longer, offering extended habitable windows. Civilizations might choose to migrate to outer planets or engineer their environments to compensate for stellar changes. They might become spacefaring, building habitats around other stars, or retreat to subterranean or virtual realms. Longevity may depend on adaptability and foresight, rather than mere technological prowess. The ethical dimension of this conversation cannot be ignored. As we search for other worlds, we must consider how our actions affect them. Planetary protection policies aim to prevent contamination of other worlds with Earth microbes and to preserve pristine environments. If we discover life, even simple microbes, questions will arise about whether and how to interact. Should we exploit resources on lifeless moons, if doing so risks unforeseen consequences? Should we attempt to terraform Mars, if microbial life exists there? These choices mirror larger themes about stewardship and responsibility. Recognizing our planet as one among many does not absolve us of caring for it. Rather, it situates our obligations within a cosmic context. Education and outreach play critical roles in sustaining interest in the search for life. Planetariums, museums, and science centers invite the public to experience the wonders of the cosmos. Schools incorporate astronomy and astrobiology into curricula, encouraging young minds to think beyond Earth. Citizen science projects like SETI at home allow anyone with a computer to contribute to data analysis. These initiatives democratize the search, bridging the gap between professional research and popular curiosity. They also foster a sense of belonging to a planetary community engaged in a collective quest. Our narrative would be incomplete without acknowledging the role of indigenous and cultural perspectives on cosmic questions. Many cultures have long contemplated relationships with the sky, with stories of star people, celestial hunters, and cosmic journeys. Modern astrobiology can learn from these traditions, which often emphasize harmony with nature and respect for other beings. Incorporating diverse voices enriches the dialogue, ensuring that the quest for life beyond Earth reflects multiple worldviews rather than a single dominant paradigm. Technological evolution is accelerating, blurring lines between biology and machines. Artificial intelligence and robotics may create new forms of intelligence that complicate definitions within the Drake equation. If machine intelligences develop self-awareness and agency, they could become interstellar explorers, free from the frailties of biology. They might traverse interstellar space over millennia, powered by nuclear batteries or solar sails, carrying the digital essence of their creators. Alternatively, biological and machine intelligences may merge, forming cybernetic societies. These possibilities broaden the meaning of intelligence and communication, suggesting that the equation's factors may need to account for post-biological evolution. On the cosmic scale, time is vast. Our civilization's technological phase spans barely a century. Dinosaurs dominated Earth for 165 million years. Stromatolite-forming microbes persisted for over 2 billion years. If intelligent civilizations arise infrequently, but last for millions of years, the galaxy could appear empty until one day we detect a signal. Alternatively, signals may have washed over Earth millions of years ago when no one listened. The overlap of communicative windows is a key parameter. Recognizing the brevity of our own window may motivate us to extend it, ensuring that future generations can continue the search and perhaps become a beacon for others. Recently, discussions of contact have embraced the notion of mutual benefit. Exchanging knowledge with an advanced civilization could revolutionize our understanding of physics, medicine, and culture. It could provide solutions to global problems or inspire new art and philosophy. Conversely, revealing ourselves could expose us to exploitation or shock. The unpredictability of contact invites both caution and hope. Many argue that the mere knowledge that we are not alone could transform human perspective, perhaps fostering global unity or humility in the face of a greater cosmos. As we refine estimates for each term in the Drake equation, we continuously adjust our expectations. The star formation rate is measured with increasing precision. Exoplanet surveys reveal that small planets are common, and studies of extremophiles make life in unusual environments seem plausible. At the same time, we remain humbled by the unknowns of abiogenesis, the contingencies of intelligence, and the perils of technological adolescence. The equation is not a static formula, but a living framework that evolves as our knowledge grows. It invites interdisciplinary collaboration, merging astrophysics, biology, chemistry, geology, anthropology, and ethics into a grand narrative. In the end, the search for life beyond Earth is as much about the search within. It challenges us to reflect on what it means to be alive and intelligent, how we care for our world and each other, and what kind of future we wish to build. It inspires awe when we contemplate the light from distant galaxies, traveling for billions of years to reach our eyes. It encourages patience, as answers may come slowly, if at all, and it fosters resilience, reminding us that even in a vast, indifferent universe, meaning can be created through curiosity, empathy, and imagination. So we continue, guided by the equation and the questions behind it. We tune our instruments, launch our probes, refine our models, and educate our children. We tell stories about other worlds and listen to the stories that indigenous peoples and ancient cultures have told. We debate the ethics of contact and consider the consequences of silence. We invest in technologies that may one day carry our descendants to other stars or bring evidence of others to our doorstep. Through it all, the gentle, slightly mysterious tone of the question persists, like a melody that repeats with variations across time and cultures. Perhaps one day, a signal will arrive, a pattern in the noise that could not have arisen from natural processes. The news will spread quickly, and for a moment, humanity will look up together. Regardless of whether we respond or remain silent, that moment will mark a turning point in the history of our species. Alternatively, centuries may pass without such a discovery, and we will continue to explore for the intrinsic joy of learning. In both cases, the Drake equation will have served its purpose, not as an oracle, but as a catalyst for inquiry, imagination, and humility. The sky above is patient. Stars burn their hydrogen quietly. Planets circle their suns in stately rhythms. Comets trace elongated arcs that ignore human timetables. Our search for company is likewise patient. We may wait for decades or millennia, but the act of waiting transforms us. It encourages us to think beyond immediate concerns, to cultivate curiosity, and to appreciate the fragility of life. In this sense, the search for life beyond Earth is an investment in both science and culture. There is also the matter of closure. Some might hope for a definitive answer within their lifetimes, but the universe does not oblige. Scientific projects often span generations. The building of cathedrals once took centuries, with artisans working on structures they would never see completed. Our cathedral is the search for life. We lay stones by conducting experiments, building telescopes, and writing code. Future generations will add their stones, and perhaps one day a spire will pierce the clouds. But whether or not we witness the completion, the act of building is meaningful. This narrative, slowly woven, attempts to mirror the pace of cosmic processes and the tone of contemplation. It began with ancient wonders and led through equations, galactic structures, chemical experiments, evolutionary tales, speculative hypotheses, and ethical dilemmas. It will continue beyond these words, because the question persists in the heart of every observer who looks up. As we end this part of our journey, we do not conclude so much as pause, breathing in the quiet between thoughts. Ahead lies further exploration, deeper dives into specific facets, and perhaps new frameworks beyond the Drake equation. For now, we rest under the stars, letting their light sink in, feeling the pull of questions that promise to accompany us for as long as we endure. Across deserts and oceans, early astronomers built observatories to measure the heavens. The ancient Nubians carved wells aligned with solstices. The ancestral Puebloans built sun-dagger markers at Fajada Butte. And Polynesian navigators memorized stars to cross vast Pacific waters. These endeavors were practical and spiritual. Survival depended on knowing seasons and directions, while rituals affirmed cultural identity. Each culture used its own languages and symbols, yet all were engaged in the same pursuit, mapping the sky to understand the world below. This universality hints at a shared human fascination that transcends time and place and links to the Drake equation's core question. Tools for observing the cosmos evolved slowly. The astrolabe allowed medieval scholars to measure star positions. sextants refined navigation, and the quadrant enabled precise altitude measurements. By combining geometry with timekeeping, these instruments laid the groundwork for understanding celestial mechanics. The telescope revolutionized astronomy, not only by magnifying, but by collecting more light, enabling detection of faint nebulae and galaxies. Each technological advance improved the resolution of our cosmic census, from naked-eye star catalogues to digital detectors that count photons. As our tools refine, so too does our ability to estimate the factors in the equation, turning speculation into measurement. Meanwhile, mathematics provided the language to describe the cosmos. The development of calculus allowed Newton to formulate the law of universal gravitation, showing that the same force that makes apples fall binds planets to stars. Later, Gauss and Riemann expanded geometry to encompass curved spaces, setting the stage for Einstein's general relativity. Probabilistic thinking emerged to handle uncertainty, offering a framework for dealing with unknown factors in the equation. Statistical methods allow us to infer exoplanet frequencies from partial detections, while Bayesian reasoning lets us update our beliefs as new data arrive. Mathematics thus acts as a bridge between observation and estimation. With the rise of electricity and radio, human technology began to emit detectable signals. Telegraphy carried messages across continents, and radio waves transmitted voices and music. These emissions leak into space, forming an ever-expanding sphere of electromagnetic noise. Earth's radio footprint now extends over 100 light-years, encompassing dozens of nearby stars. Whether this leakage is detectable depends on sensitivity and background noise, but it demonstrates that technology has made Earth visible to any listening civilization. As we shift to fiber optic communication and lower power signals, our radio brightness may fade, altering F sub C without conscious intent. The hydrogen line proposed by Cocconi and Morrison remains a compelling target, yet other frequencies may be used. The hydroxyl radical also has a line nearby, and together with hydrogen, defines a water hole region, a naturally quiet part of the radio spectrum. Civilizations might choose frequencies related to fundamental constants or to prime numbers. Laser communications at optical wavelengths offer different advantages, with narrow beams and high data rates. The search for technosignatures has expanded to include optical flashes, infrared excesses from potential Dyson spheres, and anomalies in pulsar timing. Each new method explores a different slice of parameter space, increasing the chance of detection. Project Ozma's simplicity, pointing a radio dish and listening, belied the complexity of the underlying physics. Drake had to build a receiver sensitive enough to detect weak signals amid cosmic noise. He used cryogenically cooled amplifiers to reduce thermal noise and narrow bandpass filters to isolate the hydrogen line. Even so, he encountered interference from aircraft radar and terrestrial transmitters. Today's SETI instruments use arrays of antennas, digital backends that can analyze millions of channels simultaneously, and machine learning to distinguish signals from noise. The sophistication of our searches reflects both technological growth and the recognition that interstellar communication is unlikely to be simple. When the Green Bank meeting participants estimated F sub P and N sub E, they had no exoplanet detections. They speculated that planets were common, a view supported by the nebula hypothesis of solar system formation. Their intuition proved correct, as recent surveys show that almost every star forms planets. However, the architectures vary dramatically. Some systems contain multiple super-Earths in orbits closer than Mercury. Others have giant planets on eccentric paths. Still others host resonant chains of small worlds. This diversity implies that the average number of potentially habitable planets depends on many variables, including disk mass, stellar radiation, and dynamical history. Understanding F sub L requires connecting chemistry to planetary environments. On early Earth, energy sources such as ultraviolet light, lightning, and geothermal heat likely drove the synthesis of complex organics. Hydrothermal vents provide gradients of temperature and chemistry, while tidal pools offer cycles of wetting and drying. The presence of minerals like clays could concentrate and template molecules, aiding polymerization. Some theories propose that life began in ice, where channels in frozen water could provide microenvironments for reactions. Each scenario has different probabilities and may be more or less common across planetary environments. The variety of possible paths to life complicates any estimate of F sub L. When life emerges, its evolution depends on environmental stability and variability. On Earth, mass extinctions reshaped ecosystems. They were caused by impacts, volcanism, and climate shifts. Each extinction opened ecological niches that allowed diversification. If similar cycles occur elsewhere, they could either hinder or promote the evolution of intelligence. Planets with frequent catastrophic events might reset development repeatedly, preventing complex life. Conversely, planets with long, stable periods might allow complexity to flourish. The balance between stability and change influences both of sub I and F sub C. The fraction F sub I also relates to the adaptability of organisms to changing conditions. On Earth, intelligence evolved in several lineages. Cephalopods developed problem-solving skills, birds show tool use, and mammals evolved complex social behaviors. Sociality appears to be a common driver of cognitive complexity, suggesting that cooperative pressures can select for advanced cognition. Planetary environments that encourage cooperation, such as those with patchy resources or predators requiring collective defense, might be more conducive to intelligence. However, environmental extremes could lead to strategies that favor endurance or dormancy over cognition. Thus, the path to intelligence is not inevitable, but contingent. Determining F sub C involves not only the appearance of intelligence, but also technological capability. A species might develop symbolic language, yet never invent electronics. Environmental resources matter. Without accessible metals, building circuits could be challenging. Without fossil fuels, energy might be scarce. Without transparent atmospheres, stars might be hidden, hindering astronomy. Social factors also matter. Cultural norms may discourage experimentation or limit knowledge sharing. Even if technology arises, a civilization might focus inward, exploring virtual realities or biological enhancement rather than space. These considerations suggest that F sub C could be significantly less than F sub I. Civilizations might also purposefully avoid transmission. The dark forest hypothesis posits that the universe might be filled with silent civilizations, concealing themselves to avoid predators. In such a scenario, broadcasting becomes dangerous. Alternatively, civilizations might communicate only with trusted partners or within secure networks. They could encode messages in ways we cannot interpret or embed them in cosmic structures. If hiding is the norm, then F sub C remains low, despite the prevalence of intelligence. This hypothesis underscores the importance of caution in estimating the sociological factors of the equation. As for L, civilizations must contend with external and internal pressures. External threats include astronomical events. A nearby supernova could irradiate a planet, while a passing star might disturb its orbit. Gamma-ray bursts, though rare, could sterilize large fractions of a galaxy. Planetary processes, such as volcanic eruptions, can release greenhouse gases, triggering climate change. Internally, societies face resource depletion, warfare, and the unintended consequences of technology. The transition to sustainable energy and global governance is crucial. If civilizations typically fail to manage these challenges, L might be short. If they succeed, L could be long, allowing a steady accumulation of communicators. Our understanding of the Milky Way's structure continues to deepen. Surveys such as Gaia map the positions and motions of billions of stars, revealing streams of stars from past mergers and oscillations through the galactic disk. This data allows astronomers to reconstruct the galaxy's history. The Milky Way has accreted smaller galaxies, mixing stellar populations and altering metallicity distributions. The spiral arms are not fixed structures, but density waves that stars and gas pass through. Knowing this helps refine the galactic habitable zone concept, as migrations through arms expose systems to star-forming regions and associated dangers. Metallicity gradients in the galaxy impact planet formation. Near the center, the abundance of heavy elements is high due to many generations of supernovae. However, the intense radiation and dynamic environment there can be hostile. In the outer galaxy, metallicity is lower. Fewer metals mean fewer rocky planets. Observations show a peak in the occurrence of giant planets around stars with higher metallicity. For smaller planets, the correlation is weaker, suggesting that Earth-sized worlds may form across a range of metallicities. This complexity means that the distribution of habitable planets is not uniform. It depends on local conditions shaped by the galaxy's evolution. Galactic evolution itself influences star formation rates. Feedback from massive stars, winds, radiation, and supernovae injects energy into the interstellar medium, disrupting clouds and regulating subsequent star formation. The interplay between gravity, turbulence, and magnetic fields creates cycles of collapse and dispersal. On cosmic scales, galaxy interactions trigger bursts of star formation as gas is compressed. At cosmic noon, such interactions were common. As the universe expanded, interactions became less frequent, and gas was consumed or heated, leading to the decline in star formation. These processes determine the reservoir of material available for future stars and planets. Time affects not only star formation, but also planetary system architectures. Early in the universe, high-energy radiation and frequent impacts could strip atmospheres or melt crusts. As metallicity increased, planets could form with higher masses and more complex compositions. Over billions of years, tidal forces can lock planets into synchronous rotation, freeze or thaw oceans, and drive geological activity. A planet's climate may oscillate as its orbit evolves due to gravitational interactions. Understanding these timescales helps estimate how long planets remain habitable and how this influences the evolution of life and intelligence. Cosmic history thus shapes F sub P, N sub E, and F sub L. Regions and epochs with high star formation rates may produce many planets, but intense radiation may suppress life. Later epochs may have fewer planets, but more benign environments. As star formation declines, red dwarf stars dominate. Their long lifetimes mean that conditions for life could persist trillions of years. Some models suggest that the cosmic peak of habitable planets may occur long after our sun's demise. The Drake equation, therefore, applies not only to the present, but to the entire history and future of the galaxy. In estimating F sub L, we must also consider panspermia, the possibility that life spreads from one world to another via meteorites or cometary debris. Microorganisms can survive inside rocks ejected by impacts and potentially remain dormant during interplanetary transfer. If panspermia is common, life may not need to originate independently on each planet. It could spread across planetary systems and between star systems given enough time. This would increase F sub L, because the emergence of life would need to happen only once per network. Conversely, if panspermia is rare, each world must independently generate life, potentially reducing F sub L. Moreover, the chemical diversity of exoplanet atmospheres influences our ability to detect life. Biosignatures depend on atmospheric context. For example, oxygen is a strong biosignature only when produced faster than geochemical processes can consume it. Methane can be biological or geological. Identifying life requires understanding the planet's temperature, composition, and geological activity. Spectroscopic observations will need to disentangle overlapping absorption features and consider clouds and hazes. Future missions will aim to detect such biosignatures, but interpretation will remain challenging. This uncertainty affects how we evaluate F sub L and the success of our search strategies. The Fermi paradox arises when we consider the vast numbers implied by generous values of the equation. If the galaxy should be teeming with civilizations, why do we not observe them? Many solutions have been proposed. Perhaps life is rare, or intelligence seldom leads to technology, or civilizations quickly self-destruct. Others suggest that we are one of the first civilizations, that the timing of the universe's habitability window means many potential civilizations have not yet arisen. Some propose that advanced civilizations migrate inward to access resources or outward to avoid dangers, making them harder to detect. The paradox reminds us that numbers alone do not convey the full picture. Distribution in space and time matters, as do sociological factors. Anthropic considerations caution against naive use of the equation. We exist in a universe compatible with our existence, but this does not mean that such a universe is common or likely. We cannot observe universes where life does not exist, because we cannot be there. This selection effect means that our universe's parameters, laws of physics, constants, and initial conditions may be rare among possible universes. Within our universe, we inhabit a star and planet that permit our existence. This double selection biases our perception. The Drake equation does not eliminate this bias, but it helps us be aware of it and encourages us to consider a range of scenarios. We also recognize that life and intelligence could take forms we cannot imagine. Non-carbon chemistries might emerge in exotic environments. Consciousness might arise in networks of machines. Intelligence could be distributed rather than centralized. Communication could occur via gravitational waves, neutrinos, or quantum entanglement. Our search strategies are necessarily limited by our imagination and technology. This limitation suggests that F sub c should be viewed as the fraction of civilizations detectable by our methods, not the fraction that exist. Some may communicate in ways invisible to us, and we may need entirely new physics or technology to perceive them. In confronting uncertainty, we can adopt a Bayesian approach, assigning prior probabilities to each factor and updating them as data arrive. For example, before exoplanet discovery, our prior for F sub p might have been moderate. After thousands of detections, it shifted toward 1. We might assign a wide prior for F sub L reflecting our ignorance, then narrow it if we find life on Mars or in the subsurface ocean of Europa. This approach does not yield a single answer, but a distribution of possible answers. It emphasizes that our knowledge is provisional and subject to revision. The Drake equation has cultural power beyond its scientific use. It appears in popular books, films, and songs, symbolizing humanity's curiosity. It inspires classroom discussions and science outreach events. Many people first encounter the idea that there are multiple factors determining the likelihood of extraterrestrial civilizations through this equation. By presenting a complex question in a simple form, it makes the search for life accessible. Yet its simplicity can be deceptive. Each factor hides layers of complexity. Recognizing this encourages deeper engagement and appreciation for the interdisciplinary nature of the search. In educational contexts, the equation serves as a teaching tool for scientific reasoning. Students can choose values for each factor and calculate n, then discuss how changing assumptions alters the result. This exercise illustrates how scientific models depend on assumptions and how uncertainties propagate. It demonstrates that science is not about absolute answers, but about evaluating evidence and revising models. Through this process, students learn to think critically and to appreciate the role of evidence in shaping understanding. Political and economic dimensions also influence the search. Funding for telescopes, space missions, and research grants depends on priorities set by governments and institutions. Public interest can sway these priorities. International collaboration is essential, as no single nation can support all the necessary infrastructure. Questions arise about the ownership of data, the management of potential contact, and the distribution of resources if technological breakthroughs emerge from extraterrestrial knowledge. The equation thus intersects with policy, requiring frameworks for cooperation and governance. Legal questions would also arise if we detected a signal or found life. Who would speak for Earth? Would messages require consensus from the United Nations or from a representative assembly of civilizations? How would intellectual property apply if information is shared across the stars? These questions have been discussed in documents such as the Declaration of Principles concerning activities following the detection of extraterrestrial intelligence. The equation, by highlighting the possibility of detection, brings attention to these legal and ethical considerations. The search for life also intersects with philosophy. What is the meaning of life in a universe where we are not unique? Would contact diminish or enhance our sense of significance? Philosophers have debated whether the discovery of extraterrestrial intelligence would challenge religious doctrines or inspire new ones. Some argue that it would unify humanity by providing a common context. Others fear that it could cause social unrest. These questions have no simple answers, but the equation opens space for conversation about them. Finally, the equation invites us to imagine the future of humanity. If L can be made long, if we avoid self-destruction and manage our planet wisely, we could someday become one of the communicators factored into the equation by another civilization. Our transmissions could reach stars now forming new planets. Our legacy could include messages to beings we will never meet, telling them about our world, our art, and our science. The equation thus carries a call to stewardship. By sustaining our civilization, we contribute to the cosmic chorus. We continue to refine our understanding of each factor. Upcoming missions like the Nancy Grace Roman Space Telescope will survey exoplanets using microlensing, probing populations of planets at wider separations. The Extremely Large Telescope will image exoplanets and analyze their spectra, providing data on atmospheres and surfaces. Projects like Europa Clipper and Dragonfly will explore icy moons, searching for signs of life. Laboratory work on prebiotic chemistry will test pathways from simple molecules to complex polymers. Advances in computing will enable simulations of galaxy evolution and climate modeling for exoplanets. Each discovery will narrow uncertainties and inform our estimates. The interplay between scientific progress and public imagination will shape how the equation evolves. Breakthroughs will capture public attention, inspiring new stories and art. Fiction will continue to explore alternative biochemistries, civilizations, and contact scenarios. As our picture of the universe becomes richer, our cultural expressions will diversify. The equation will remain a touchstone, linking science and culture and reminding us of the big question that underlies them both. In the coming decades, our ability to detect biosignatures may improve dramatically. Instruments capable of blocking starlight and detecting Earth-sized planets around sun-like stars will become a reality. High-resolution spectroscopy will reveal the atmospheric composition of these worlds. We may find planets with oxygen, methane, or other gases out of equilibrium, raising excitement about life. Alternatively, we may see featureless spectra, suggesting barren worlds or atmospheres dominated by gases produced abiotically. Each result will inform F sub L and refine our search strategies. As we interpret data, we must remain vigilant against false positives. Some abiotic processes can produce oxygen or methane. Stellar activity can mimic signals. Instrumental artifacts can masquerade as spectral features. The history of exoplanet detection includes retracted claims and misinterpretations. Rigorous verification and multiple lines of evidence are essential. This caution extends to technosignatures. Repeating signals can be caused by satellites or other terrestrial sources. Only through careful analysis and independent confirmation can we claim a detection of life or intelligence. Our exploration of the cosmos has taught us humility. When we first thought Venus might be a swamp and Mars a world of canals, we were projecting Earth-like features onto other planets. We now know that planetary diversity exceeds our early imagination. Similarly, our expectations of life and intelligence may be Earth-centric. The Drake equation encourages us to quantify our assumptions and to be open to surprises. It invites us to listen and look with the broadest possible perspective, to avoid narrow expectations that could cause us to miss the unexpected. The equation also prompts us to think long-term. Civilizations that persist must plan for events that unfold over thousands or millions of years. The evolution of stars, the drift of continents, the accumulation of atmospheric changes. They must develop technologies and social structures that are adaptive and resilient. As we consider F sub C and L, we reflect on whether we are laying foundations for a long-lived, communicative civilization. Education, sustainability, and cooperation become as essential as technology. There is also a personal dimension. Each person's curiosity contributes to the collective quest. Reading, learning, discussing, and supporting science fosters a culture that values exploration. You need not be an astronomer to participate. You can be a teacher inspiring students, a writer creating stories, or a citizen advocating for research funding. The Drake equation belongs to all of us because it asks a question that touches everyone. Are we alone? And what does it mean if we are not? It invites each person to engage with the cosmos in their own way. The cosmic perspective gained by contemplating the equation can inform everyday life. Recognizing that we share a fragile planet with all its life can inspire environmental stewardship. Understanding that our differences are small compared to the scale of the universe can promote tolerance and empathy. Seeing ourselves as part of a cosmic story can provide meaning and purpose. These lessons do not require contact with aliens. They emerge from the very act of asking the question and considering its implications. When we imagine other civilizations, We project our hopes and fears. We imagine wise beings who have overcome their destructive impulses and who offer us guidance. We also imagine threats, invasions, and existential risks. These projections reflect our inner state as much as external realities. The equation provides a framework for grounding these imaginings in data, but it cannot eliminate the human tendency to weave stories. Recognizing this interplay between fact and fiction enriches our understanding and reminds us to be aware of our biases. In the centuries ahead, humanity may send probes to nearby stars. Concepts like light sails propelled by lasers could accelerate tiny spacecraft to a significant fraction of the speed of light. Such probes could reach the closest star systems within decades, returning images and data. The results would revolutionize our understanding of exoplanets and could provide direct evidence of life. If we find signs of life, we may eventually send slower, larger probes capable of sampling or interacting. These efforts extend the equation into the realm of active exploration, making us not just listeners, but explorers. The search for life also motivates the preservation of languages, cultures, and knowledge. If we send messages into space, what aspects of humanity do we include? Our art, science, stories, and languages represent the diversity of our species. Preserving them for future generations and for potential extraterrestrial audiences becomes a responsibility. The equation, by suggesting that others may one day know of us, encourages us to curate our legacy thoughtfully. Ultimately, the Drake equation is about curiosity. It is a mathematical expression of the human urge to seek companions in the vastness of space. It quantifies the unknown, not to diminish wonder, but to channel it into inquiry. As our instruments and knowledge improve, as we refine each factor, the equation remains a living framework. It grows with us, reflecting our evolving understanding of the universe and our place within it. It invites us to listen, to watch, to think, and to dream, knowing that the cosmos holds more mysteries than we can yet imagine. Cosmic rays and high-energy particles whisper stories about the galaxy's more violent processes. Accelerated in supernova remnants and active galactic nuclei, these particles traverse space and occasionally strike planetary atmospheres, generating showers of secondary particles and altering atmospheric chemistry. On Earth, cosmic rays may have contributed to cloud formation and even influenced mutation rates, nudging evolution. Worlds closer to the galactic center, or more active star-forming regions, might experience higher cosmic ray fluxes, impacting their habitability and potentially affecting F sub L. Understanding these energetic messengers connects astrophysics to planetary environments, providing another layer to the equation. Neutrinos, ghostly particles that rarely interact with matter, stream from nuclear reactions inside stars and supernovae. They pass through planets and our bodies unnoticed, carrying information about their sources. Detecting neutrino bursts from distant events requires massive detectors buried deep underground or underwater. If advanced civilizations harness neutrinos for communication, we might not be looking in the right place. Considering neutrino-based technosignatures expands of subsea into realms beyond our current detection capabilities. It reminds us that there may be channels of communication we have yet to imagine. Gravitational waves, ripples in spacetime predicted by Einstein and detected only in the past decade, open another window on the cosmos. They reveal collisions of black holes and neutron stars, events that illuminate the life cycles of massive stars and the production of heavy elements like gold and platinum. While gravitational waves are unlikely to carry intentional messages, their detection informs our understanding of stellar populations and the frequency of cataclysmic events. These insights feed back into R star, F sub P, and the hazards influencing L, linking fundamental physics to the search for life. Magnetic fields thread galaxies, shaping the motion of charged particles and influencing star formation. Within planetary systems, magnetic fields shield atmospheres from stellar winds. Earth's magnetosphere deflects charged particles, preserving our air and water. Mars lost its magnetic field early and subsequently lost much of its atmosphere. For exoplanets around active stars, a magnetic field could be crucial for habitability. Studies of stellar activity, planetary magnetic dynamos, and magnetosphere interactions contribute to assessments of N sub E and F sub L. They add nuance to the simple habitable zone concept and illustrate the importance of planetary interiors. The classification of stars into spectral types, O, B, A, F, G, K, M, provides a framework for evaluating R star and N sub E. O and B stars are massive and short-lived. They burn brightly and die young, often exploding as supernovae that enrich their surroundings but leave little time for life to evolve. A and F stars live longer, but still only hundreds of millions to a few billion years. G-type stars like the Sun offer several billion years of stability. K and M dwarfs are even longer lived, but their flares may pose challenges. Understanding the distribution of these stars and their planetary systems helps refine estimates of the number of potentially habitable worlds. Planetary atmospheres evolve over time through outgassing, impacts, and interactions with stellar radiation. Early atmospheres may be rich in hydrogen and helium, but these light gases escape into space unless gravity is strong. Volcanism releases water vapor, carbon dioxide, sulfur compounds, and other gases, while impacts can strip or deliver volatiles. The balance between greenhouse warming and albedo determines surface temperatures. The presence of a magnetic field, tectonic activity, and biotic processes further modify atmospheres. Modeling atmospheric evolution across different planetary masses and stellar environments informs N sub E and F sub L, revealing which worlds might sustain liquid water and support metabolism. Life itself can alter planetary conditions, creating feedbacks that stabilize or destabilize climate. On Earth, photosynthetic organisms transform the atmosphere by producing oxygen, enabling the evolution of complex aerobic life. Microbes regulate nutrient cycles, while vegetation influences albedo and water cycles. The Gaia hypothesis posits that life and the environment co-evolve to maintain habitable conditions. If similar processes occur elsewhere, biospheres may expand the boundaries of the classical habitable zone, increasing N sub E. Conversely, life could also trigger runaway changes that lead to extinction. Investigating biospheric feedbacks broadens our understanding of life's role in planetary systems. Biological diversity on Earth suggests that life could adapt to environments we once thought inhospitable. Thermophiles thrive in boiling hot springs. Psychrophiles inhabit Antarctic ice. Acidophiles live in battery acid-like conditions. Barophiles endure crushing pressures in deep trenches. These extremophiles demonstrate that life can exploit various energy sources and withstand extreme temperatures, pH levels, and pressures. Extrapolating from extremophiles allows us to imagine life in the subsurface oceans of icy moons or in the atmosphere of Venus. Each new discovery of an extremophile expands for sub-L by revealing that the potential habitats for life are broader than previously thought. Communication among non-human species shows complex forms of information exchange. Bees perform dances to convey the direction and distance of flowers. Whales sing intricate songs. Birds mimic sounds. Ants use chemical trails. These behaviors are adapted to specific sensory modalities and ecological niches. If intelligence arises elsewhere, its communication systems may be shaped by environments we cannot easily imagine. A species living in a dense atmosphere might use low-frequency sound. One in a methane ocean might use chemical signals. Recognizing this diversity reminds us that our search for signals must be flexible, and that F sub C depends on more than technology. Artifacts and structures could outlast the civilizations that built them, serving as techno-signatures long after their creators vanish. On Earth, the Great Pyramids and the ruins of ancient cities endure for millennia. In space, orbital debris and satellites will persist for centuries. On other worlds, colossal structures like rings or mirrors might modify the light of a star. Theoretical constructs like Dyson spheres, vast arrays of orbiting platforms capturing starlight, could be detectable through anomalies in stellar spectra. Searching for such megastructures expands F sub C by considering passive signatures of technology, not just active transmissions. Biochemical possibilities extend beyond Earth's carbon-water paradigm. Alternative solvents like ammonia or formamide could support chemical networks, though their temperature ranges and solvent properties differ from water. Hydrocarbons, as found on Titan, could provide liquid environments at low temperatures. Some researchers explore the potential of supercritical carbon dioxide or ionic liquids as solvents. Each alternative environment would produce different reaction rates and molecular structures. Studying these possibilities informs F sub L by revealing that life may arise under conditions distinct from those on Earth. Time travel, in the sense of signals crossing large cosmic distances, shapes our perception of the universe. When we observe a star 10,000 light-years away, we see it as it was 10,000 years ago. Similarly, any signal we send or receive carries information from different epochs. This temporal aspect affects communication. A civilization might send a message, but by the time it arrives, both sender and receiver could have changed. Understanding time delays encourages patience and shapes strategies for sending and receiving messages. It also means that the factor L must account for temporal overlap of communicating epochs. The search for extraterrestrial intelligence intersects with the concept of the Great Filter, a hypothetical barrier in the progression from simple life to advanced civilizations. The filter could be in the past, making the emergence of life or intelligence rare, or in the future, making self-destruction likely. Pinpointing where the filter lies affects our estimates of F sub L, F sub I, and L. If we discover simple life widely, but no intelligence, the filter may lie in the development of intelligence. If we detect many signals, the filter might be behind us, implying that life and intelligence are common. The Great Filter adds a layer of existential significance to the equation. Exomoons, moons orbiting planets in other star systems, represent another class of potential habitats. Large moons of giant planets could have stable climates, tidal heating, and protective magnetospheres. They might have day-night cycles different from their planets, influencing climate and biology. Detecting exomoons remains challenging, but upcoming telescopes may reveal them through transit timing variations or direct imaging. Including exomoons in N sub E increases the number of potential habitable environments and shows that the concept of a planet is not the only unit of astrobiological interest. Free-floating planets, ejected from their systems during formation, drift through interstellar space. Though they lack sunlight, they could retain thick atmospheres and internal heat, maintaining subsurface oceans. Radioactive decay and tidal heating from moons could provide energy. If life emerges in such environments, its conditions would be isolated but potentially stable for long periods. Detecting free-floating planets requires careful microlensing surveys, but their existence increases the number of habitats, affecting N sub E and F sub L. Climate stability is crucial for sustained evolution. On Earth, the carbon-silicate cycle regulates atmospheric carbon dioxide, acting as a thermostat over geological timescales. Tectonic activity recycles carbonates into the mantle, where volcanic outgassing returns CO2 to the atmosphere. Without plate tectonics, a planet might lose its ability to regulate climate, becoming a frozen snowball or a runaway greenhouse. The presence of continents, oceans, and a balance between erosion and volcanism shapes this cycle. Considering such geochemical cycles helps identify planets with long-term climate stability and thus higher F sub L and F sub I. Planetary interiors influence magnetic fields, tectonics, and volcanic activity. The size and composition of the core, the presence of a liquid outer layer, and rotation rate determine whether a planet generates a magnetosphere. Plate tectonics, driven by mantle convection, recycles materials and creates mountain ranges, influencing weathering and climate. Volcanism releases gases and builds new crust. On Mars, the lack of plate tectonics contributes to its static crust and thin atmosphere. Understanding planetary interiors through models and measurements informs our assessment of which planets might be geologically active and hospitable. The emergence of life might be tied to cycles of environmental stress. On Earth, periods of glaciation, volcanic eruptions, and meteor impacts have imposed bottlenecks on populations. Such pressures can drive evolution by selecting for adaptability and innovation. If similar cycles occur elsewhere, they could accelerate or hinder the development of complex life and intelligence. This perspective suggests that dynamic planets with moderate variability might be more conducive to evolutionary innovation than perfectly stable worlds. Astrobiology also considers the potential for life in cosmic structures beyond planets. In dense molecular clouds, small bodies like comets and asteroids could harbor prebiotic molecules. During planetary system formation, these bodies deliver organics and water to young planets. Some theories propose that life could exist in clouds of plasma, inside stars, or in the atmospheres of gas giants, though these ideas remain speculative. Exploring such unconventional habitats expands our sense of where to look and influences the breadth of F sub L. Even within the solar system, potential biospheres remain unexplored. Mars, once wetter and warmer, may still host microbial life underground. Venus's cloud decks contain mysterious chemistry and unusual particles. The subsurface oceans of Europa, Ganymede, Enceladus, and Titan hold promise. Each environment requires tailored instruments and missions. Discovering life or biosignatures in our backyard would profoundly influence F sub L and inform our expectations for exoplanets. Conversely, finding sterile worlds could imply that life is rarer than we hope. Our ability to model climates, planetary interiors, and biospheres depends on computing power and algorithms. Advanced simulations can couple atmospheric dynamics, ocean currents, and radiative transfer to predict climate evolution. Machine learning assists in sifting through data for exoplanet detection and classification. As these tools improve, they enhance our capacity to estimate the factors of the equation. They also illustrate the symbiotic relationship between technology and theory. Better tools yield better models, which in turn guide the design of new tools. Human perspectives on the search for life are influenced by philosophical and religious beliefs. Some traditions anticipate extraterrestrial life, viewing it as part of a divine creation. Others emphasize human uniqueness. The discovery of life elsewhere could challenge or enrich these perspectives. Engaging with diverse viewpoints ensures that the search is inclusive and sensitive to cultural contexts. The equation, by providing a scientific basis for speculation, can foster dialogue across disciplines and cultures. The question of whether to actively send messages divides the SETI community. Messaging to extraterrestrial intelligence, METI, advocates argue that proactive outreach could break the cosmic silence and demonstrate our curiosity. Critics warn that we do not know who might receive the message and what their intentions might be. The debate touches on ethics, risk assessment, and the value of curiosity. Each position implies different assumptions about F sub C and L and reflects underlying attitudes toward the unknown. Looking further ahead, we can imagine civilizations that migrate through the galaxy, colonizing or sampling multiple star systems. Such civilizations could create networks of probes or habitats, leaving behind artifacts and signals. Their expansion would alter the distribution of life and intelligence, impacting F sub I and F sub C over time. Whether such expansion is feasible or desirable depends on technological capabilities and values. Considering expansionist scenarios broadens our understanding of possible life trajectories. In summary, the Drake equation encompasses an immense array of scientific, cultural, and philosophical issues. Each factor represents a frontier of research and reflection. As we continue to learn, we refine our estimates, update our models, and adjust our expectations. The equation remains a beacon of curiosity, guiding us through the darkness and linking our questions to the cosmos. Our journey has just begun, and the quiet question will continue to inspire exploration, conversation, and wonder. The stars that twinkle above have whispered to us for as long as we have been able to lift our eyes. They adorn the night like beads on an infinite tapestry, and they have given storytellers a stage on which to project human hopes, fears, and questions. Around campfires and within ancient temples, people wondered not just about their own place in the cosmos, but about whether anyone else could also be looking up. Those early questions were more poetic than scientific, yet they planted a seed that would one day become the Drake equation. When sailors navigated by the stars, or farmers timed their seasons by the rising constellations, they were paying attention to patterns that seemed regular and ordered. Behind the predictable motion, there was always a hint of the unknown, a sense that beyond our small world, there must be other worlds. Philosophers of antiquity speculated about a multiplicity of universes and about inhabited worlds, yet they could do little more than speculate, because the technology to detect other planets did not exist. The night sky was a canvas of mystery, inviting us to imagine companions in the dark. As centuries rolled by, curiosity evolved alongside observation. In ancient Babylonia and Greece, astronomy was bound to myth and measurement. The positions of planets inspired both astrology and early geometry. Later, Islamic astronomers refined instruments and recorded star positions with precision, preserving knowledge through periods when other parts of the world lost it. In China, imperial observatories kept watch on comets and novae, seeing the heavens as part of an emperor's realm, while in Mesoamerica, the motions of Venus and the Sun were woven into calendars that guided agriculture and ritual. Across cultures, the night was a laboratory where imagination and observation began to converge. The invention of the telescope at the start of the 17th century changed everything. Suddenly, the fuzzy disk of Saturn sprouted rings, and Jupiter revealed moons. confirming that not all celestial bodies revolved around the Earth. Galileo's telescope was small, but it extended human senses beyond previous limits and opened a new way of seeing. With each improvement, from Newton's reflecting mirror to Herschel's giant reflectors, astronomers probed deeper into the cosmos and saw fainter and more distant objects. Their expanding universe did not yet contain other civilizations, but it widened the stage on which those civilizations could be imagined. By the 19th century, scientists had begun to study planetary atmospheres and to compare worlds. William Whewell coined the word astrobiology when speculating about life on other planets, and Percival Lowell later saw canals on Mars where none existed. The absence of evidence did not deter speculation. If anything, it encouraged it. Writers such as H.G. Wells turned scientific observations into stories about invading Martians, while philosophers like Fontenelle wrote dialogues describing inhabitants of other stars. Imagination outran reality, yet it prepared human minds to accept the idea that life might be a cosmic phenomenon rather than a terrestrial anomaly. When wireless telegraphy and radio communication developed in the early 20th century, a new possibility emerged. Perhaps we could listen for signals from afar. Guglielmo Marconi and Nikola Tesla dreamed of messages from Mars, and radio astronomers began to consider frequencies that might carry interstellar conversations. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a brief paper suggesting that the narrow spectral line emitted by neutral hydrogen at a wavelength of 21 centimeters would be a logical frequency for intelligent beings to use for communication. Because hydrogen is the most abundant element in the universe, its spectral line is a universal marker, and any technologically capable species would be familiar with it. This idea took root in the mind of a young radio astronomer named Frank Drake. In 1960, he persuaded the National Radio Astronomy Observatory in Greenbank, West Virginia, to let him use their 85-foot dish to conduct Project Ozma, the first systematic search for radio signals from nearby stars. He tuned his receiver to the hydrogen line and listened to Tau Ceti and Epsilon Eridani, two sun-like stars. For months, he heard only silence and occasional human-made interference. But the very act of listening marked the beginning of observational SETI. The project cost little and yielded no detection, yet it proved that the search could be done and that the technology existed to attempt it. After Project Ozma, Drake was asked to organize a small conference to discuss how to search for extraterrestrial intelligence. In the fall of 1961, a handful of scientists gathered in Greenbank's conference room. Biologists like Joshua Lederberg, astrophysicists like Philip Morrison, chemists like Melvin Calvin, and the young astronomer Carl Sagan. Drake wrote on the blackboard an equation he had devised to structure the discussion. N equals R, star times F sub P times N sub E times F sub L times F sub I times F sub C times L. The product of these factors would estimate the number of communicating civilizations in our galaxy. He never intended the equation to give a precise answer. Rather, it was a way to break a huge question into manageable pieces. The first factor, R star, represents the rate at which stars suitable for life are born in the Milky Way. In 1961, astronomers knew roughly how many stars formed each year because they could count stars of different ages and model the gravitational collapse of gas clouds. The rate is not constant over cosmic time. In the early universe, star formation was furious, peaking a few billion years after the Big Bang, and then declining to just a small percentage of its peak. Our galaxy still produces new stars, but at a slower pace, like embers glowing after a fire. The second factor, F sub P, asks what fraction of stars have planets. For centuries, this was pure conjecture. Now we know that most stars host planets of various sizes and compositions. The discovery of exoplanets began in the 1990s with pulsar planets and hot Jupiters, and today thousands have been found using transits, radial velocity, and microlensing. From data collected by the Kepler spacecraft, we infer that about 1 in 5 Sun-like stars hosts an Earth-sized planet in the habitable zone where liquid water might exist. Even low-mass red dwarfs, though prone to flares, harbour planets, some of which may be tidally locked, with one face perpetually facing their star. The third factor, n sub e, considers the average number of planets per star that could support life. This is not just about being the right distance from the star. It also involves planetary composition, atmosphere, and internal dynamics. A world must be massive enough to hold an atmosphere, but not so massive that it becomes a gas giant. It should have water, or another solvent, to facilitate chemistry. Moons around gas giants and free-floating planets heated by radioactive decay could also provide niches for life. Our own solar system has multiple worlds with subsurface oceans, including Europa and Enceladus, reminding us that habitable zones are not limited to orbits in the plane. After n sub e comes f sub l, the fraction of those potentially habitable worlds on which life actually arises. Here we confront our profound ignorance. Life emerged on Earth relatively quickly after the planet cooled, but we cannot tell whether that rapid appearance is typical or rare. Laboratory experiments show that organic molecules can form under a range of conditions, but the leap from complex chemistry to self-replicating systems remains mysterious. Some researchers think life may emerge easily wherever there is energy, water, and carbon. Others argue that the transition from chemistry to biology could be extremely improbable, making life exceedingly rare. Then comes f sub I, the fraction of life-bearing planets on which intelligence evolves. Evolution is not goal-directed. It responds to local conditions. On Earth, many organisms are well adapted without having human-like cognition. Intelligence in our sense, symbolic thought, language, technology, may require specific evolutionary pressures and the presence of stable environments over long timescales. Even if intelligence appears, there is no guarantee it will develop technology capable of interstellar communication, which leads to f sub c, the fraction of intelligent species that release detectable signals. A civilization might choose to remain quiet, or its technology could be based on means we cannot detect, such as communication through particles or dark matter. The final term, L, represents the longevity of a communicating civilization. This factor could dominate the value of N. If civilizations tend to self-destruct or to lose interest in communication, then L is short, and the number of simultaneous communicators is small. If civilizations survive for millions of years, L is long, and the galaxy could be buzzing with messages. At the Green Bank meeting, the participants debated what values to assign to each factor. They knew our star fairly well, but beyond that, the ranges were guesswork. Yet by multiplying plausible numbers, they showed that a galaxy with billions of stars could plausibly host many communicators. To unpack each term requires understanding astrophysics, planetary science, biochemistry, evolutionary biology, and sociology. Starting with our star, we consider how stars form. Stars are born when cold clouds of gas and dust collapse under their own gravity. In the densest parts of these clouds, fragments condense into protostars that heat up and ignite nuclear fusion. Most stars form in clusters, and their masses range from cool red dwarfs to hot blue giants. The distribution of stellar masses, the initial mass function, favors low-mass stars, meaning that long-lived red dwarfs are common. These small stars burn slowly, providing stable energy for tens of billions of years. But their intense flares and close-in habitable zones raise questions about planetary atmospheres and radiation. The star formation rate is not uniform across the galaxy. It is highest in regions rich in gas and dust, such as spiral arms. Research on the Milky Way's structure shows that metallicity, the abundance of elements heavier than hydrogen and helium, increases towards the center. Higher metallicity means more solid material to build planets, yet the inner galaxy also hosts more supernovae and gamma-ray bursts, which can sterilize planets. Our Sun orbits at a distance where there is enough metal to form rocky worlds and fewer catastrophic events. The concept of a galactic habitable zone suggests that life is most likely in a ring around the galaxy where conditions are balanced, though recent studies argue that stars migrate and that habitability may be more dynamic. Over cosmic time, star formation has waxed and waned. During the epoch known as cosmic noon, roughly 2 to 3 billion years after the Big Bang, galaxies formed stars at rates 10 to 100 times higher than today. Researchers describe this period as one where galaxies grew rapidly, merging with neighbors, forming disks, and building the majority of their stellar mass. After cosmic noon, the overall star formation rate declined as gas supplies were consumed and energy input from supernovae and active galactic nuclei heated the interstellar medium. Today, the universe's star formation rate is only a fraction of its peak, but stars still form in pockets of dense gas, providing new opportunities for planets and life. The fraction f sub p has become less uncertain thanks to exoplanet surveys. At the time of the Green Bank meeting, planets outside the solar system were purely speculative. Now we know of a menagerie: hot Jupiters hugging their stars, super-Earths with thick atmospheres, mini-Neptunes, and planets in multi-resonant chains. These discoveries show that planetary systems are diverse and often unlike our own. In some, giant planets migrate inward and disrupt the formation of terrestrial worlds. In others, systems remain stable for billions of years. Understanding f sub p involves exploring how disks of gas and dust around young stars evolve, how planets accrete from dust grains into protoplanets, and how gravitational interactions sculpt final orbits. Determining n sub e requires assessing which of these planets are truly habitable. The classical habitable zone is defined as the range of distances from a star where surface liquid water could exist. But this concept hides complexity. A planet's greenhouse gases, albedo, rotation rate, and internal heat all affect its surface conditions. Venus receives only slightly more sunlight than Earth, yet its dense carbon dioxide atmosphere creates a runaway greenhouse effect that makes its surface hotter than melting lead. Mars lies at the edge of the habitable zone, but is cold and thin-aired. Moons like Europa and Enceladus lie outside the habitable zone, yet harbour subsurface oceans kept warm by tidal heating. Thus, n sub e could include a wide variety of environments. We can only guess at f sub l. Laboratory experiments replicate aspects of prebiotic chemistry. Miller-Urey type experiments show that amino acids can form from simple gases and energy sources. Hydrothermal vent models suggest that mineral surfaces could catalyze the formation of self-replicating molecules. Meteorites deliver complex organics to planets, and interstellar clouds contain sugars and amino acids. These clues indicate that organic chemistry is widespread. Still, the jump to life might require improbable circumstances, perhaps a sequence of events that occurred once in our galaxy. Without data from other biospheres, f sub l remains uncertain. Life requires more than chemistry. It needs a solvent. On Earth, that solvent is water, which has unique properties. Water is polar, dissolving salts and enabling ions and molecules to move and interact. It forms hydrogen bonds that stabilize DNA and proteins, and it remains liquid across a broad temperature range. Its solid phase floats on its liquid phase, insulating oceans against freezing, and its high heat capacity moderates climate. Other solvents like ammonia or methane have narrower liquid ranges and weaker hydrogen bonding. Some scientists speculate that life could arise in methane lakes, such as those on Saturn's moon Titan, but such chemistries would operate at very low temperatures, slowing reactions. Silicon-based life is often imagined in fiction, but silicon-carbon bonds are less stable, and silicon dioxide is a solid, making waste disposal problematic. To define life, NASA adopted the working definition: a self-sustaining chemical system capable of Darwinian evolution. This definition captures two key aspects: self-sustaining, meaning that a system can grow, reproduce, and maintain itself, and Darwinian evolution, meaning that heritable variation allows adaptation through natural selection. This definition is broad enough to encompass potential non-Earth life, while being precise enough to exclude non-living chemical processes. It focuses on populations rather than individuals, acknowledging that evolution operates on groups over generations, not on single organisms. Using this definition, we can evaluate environments by asking whether they could support sustained chemical networks and evolutionary processes. On Earth, life's essential chemistry is carbon-based. Carbon atoms form long chains and rings, creating a vast variety of molecules, from sugars to nucleic acids. Carbon's ability to make 4 stable covalent bonds provides structural flexibility unmatched by other elements. The existence of chiral molecules, molecules that are mirror images of each other, and the uniform chirality in biological systems demonstrate chemical selectivity that might be universal or a result of chance. Silicon, though in the same group of the periodic table, forms weaker bonds and prefers to bond with oxygen. Silicon dioxide is a solid, making it difficult for hypothetical silicon life to excrete waste. This chemical reasoning suggests that while alternative biochemistries are conceivable, carbon and water remain the most plausible basis for life as we know it. Once life appears, evolution can explore myriad paths. Simple cells may diversify into complex multicellular organisms, and intelligence may or may not arise. On Earth, for 3 billion years, life was microbial. Only 500 million years ago did complex animals emerge, and only recently did human-like intelligence appear. There is no guarantee that intelligence is inevitable. It might be a contingent outcome of particular environments and random evolutionary experiments. If intelligence arises, does it necessarily lead to technology? Dolphins, elephants, and corvids are intelligent, but do not build radios. Technology requires not only cognitive capacity, but also manipulative ability and a social structure that fosters cumulative knowledge. Even with technology, a species might not broadcast its presence. Early human broadcasts leaked into space. Radio and television transmissions could be detected from nearby stars. But as technology advances, communication often becomes more efficient and less detectable, using fiber optics and highly directional beams. Civilizations may choose to avoid broadcasting for fear of danger, or they may communicate in ways we cannot imagine. Some might focus on interstellar beacons or purposeful messaging. Others might remain silent or communicate only within their planetary system. The factor F sub c thus embodies cultural choices as much as technological capability. The longevity term, L, invites reflection on sustainability. Human civilization has existed for thousands of years, but our technological phase spans less than 2 centuries. We face challenges such as nuclear proliferation, climate change, and resource depletion. If other civilizations encounter similar challenges, perhaps many self-destruct before they can sustain long-term communication. Alternatively, some may transition to sustainable modes, harnessing renewable energy, managing ecosystems, and mitigating dangers from asteroid impacts or stellar evolution. The value of L could thus vary widely across civilizations, dominating the equation's outcome. As the meeting in Green Bank unfolded, participants brought expertise from their fields. The Nobel laureate chemist Melvin Calvin thought about chemical evolution. The biologist Joshua Lederberg considered microbial life in the universe. The physicist Philip Morrison had co-authored the paper that inspired the search frequency. Carl Sagan, then a young astronomer, would later popularize the equation in his books and television series. The group recognized that each factor spanned disciplines and that collaboration was essential. Their discussions were lively, speculative, and grounded in data where available. In the end, they did not produce a number to be carved in stone, but they left with a framework that continues to guide research and stimulate imagination. The Milky Way, our home galaxy, is a barred spiral containing hundreds of billions of stars. Its central bulge hosts older, metal-poor stars, while the disk harbors younger, metal-rich populations. Spiral arms are sites of active star formation, with bright nebulae and clusters. The Sun lies in the Orion Spur, between 2 major arms, about 27,000 light-years from the galactic center. Its orbit is nearly circular and co-rotates with the spiral pattern, meaning that it rarely passes through the arms. This orbit reduces our exposure to supernovae and allows long periods of stability. The notion of a galactic habitable zone arises from these considerations. Too close to the center, and stars experience intense radiation and gravitational perturbations. Too far out, and there may be insufficient heavy elements to build planets. Recent work suggests that the concept of a static habitable zone may be too simplistic. Stars migrate over time, moving inward and outward due to interactions with spiral arms and giant molecular clouds. The Sun itself may have formed closer to the galactic center and migrated outward. As stars migrate, they encounter different radiation environments, supernova rates, and metallicities. Some orbits may be safer over long periods, while others may pass through hazardous regions. Thus, instead of a fixed ring, we might think of galactic habitable orbits, where conditions remain favorable over billions of years. This dynamic view recognizes the complexity of galaxy evolution and the importance of time as a variable. Time enters the equation in multiple ways. The star formation rate has changed throughout cosmic history, affecting the number of planets formed at different epochs. Early galaxies were smaller, more chaotic, and enriched with heavy elements more slowly. As cosmic time progressed, supernovae seeded interstellar space with metals, enabling the formation of rocky planets. Cosmic noon saw the universe producing most of its stars and black holes, after which star formation declined. Life requires time to evolve. If a planet forms too early, heavy elements may be scarce. If it forms too late, the window for complex life may close as low-mass stars dominate and high-energy radiation declines. The distribution of possible civilizations in time may thus be skewed towards certain cosmic epochs. On shorter timescales, stellar lifetimes matter. Massive stars burn quickly and explode as supernovae, sterilizing nearby planets, but enriching space with elements. Medium-mass stars like the Sun live billions of years, providing long, stable epochs. Red dwarfs can burn for trillions of years, offering long potential lifetimes for life to evolve. However, their intense flare activity could strip planetary atmospheres, and their habitable zones are so close that planets may be tidally locked. If life can adapt to flares and tidally locked climates, red dwarf systems could host civilizations long after sun-like stars fade. Time, therefore, is not just the age of the universe, but also the lifespans of individual stars and planetary environments. The Drake equation is not a deterministic formula, but a scaffold for thought. Each factor represents a question whose answer ranges across orders of magnitude. By updating our estimates as data accumulate, through exoplanet surveys, studies of star formation, research on the origin of life, we refine our sense of the possible. Uncertainty is not a defect. It is a feature that encourages humility and curiosity. The equation invites us to consider both optimistic and pessimistic scenarios, to examine our assumptions, and to recognize our ignorance. It prompts discussions about the future of our civilization and about what we might learn from eventual contact, or the absence of contact, with others. In thinking about life elsewhere, we must also consider detection. Detecting life remotely involves looking for biosignatures, such as atmospheric gases that are out of equilibrium. Oxygen and methane together can indicate biological activity because they react and would not coexist without continuous replenishment. The ladder of life detection, developed by astrobiologists, lists features that can be measured and how specific they are to life. At lower rungs are features like organic molecules, which could form abiotically. Higher rungs involve patterns of chemical disequilibrium and isotopic ratios that are difficult to explain without biology. For intelligent life, technosignatures become relevant. Radio transmissions, laser pulses, megastructures that alter starlight. Searching for technosignatures broadens our perspective beyond the hydrogen line to encompass all possible detectable technologies. Another consideration is our own bias. We are one example of intelligent life, and we inhabit a particular type of planet around a middle-aged star. Our sample size is 1. This makes it tempting to generalize from our experience. Yet our existence might be unusual. Perhaps intelligent life is common, but rarely builds technology. Or perhaps it is rare, but long-lived when it appears. The anthropic principle suggests that we observe our environment because it permits our existence. If intelligence were too rare, we would not be here to ask these questions. However, this principle does not provide numerical answers. It simply reminds us that selection effects shape our perspective. We must therefore remain cautious when extrapolating from our singular example. Cosmic hazards also influence L. Supernovae and gamma-ray bursts can irradiate planets, stripping atmospheres and sterilizing surfaces. Close encounters with passing stars can perturb planetary orbits, triggering climate changes. Impacts from asteroids or comets can reset evolution, as happened with the dinosaurs. Planets may suffer runaway greenhouse effects, global ice ages, or volcanic supereruptions. Civilizations may face self-made hazards, such as nuclear war or environmental collapse. The survivability of a civilization thus depends not only on planetary conditions, but also on cosmic and self-inflicted dangers. Understanding these risks informs our estimate of how long communicators might endure. The equation also invites cultural reflection. The decision to listen or to transmit involves values and ethics. Some argue that broadcasting our presence could endanger us by alerting hostile civilizations. Others say that a long silence across the galaxy may itself be a sign that communication is safe. The content of a message would reflect a civilization's knowledge and values. Would we send mathematical truths, images, or music? How would we interpret a signal that arrives? The search for extraterrestrial intelligence is not just a scientific endeavor. It is a philosophical and cultural one. It requires thinking about how we represent ourselves and how we might respond to the other. If we do detect a signal, the implications would be profound. Even a simple beacon would prove that we are not alone, reshaping religion, philosophy, and our sense of place. It could provide knowledge beyond our current understanding, or simply demonstrate that intelligence has arisen elsewhere. If the signal contains information, decoding it could take years or decades. Meanwhile, we would have to decide how to respond, if at all. The process would demand international cooperation, because no single nation or institution would own such a discovery. The moment of detection would mark a transition in human history akin to the Copernican revolution, but with cosmic consequences. However, if we listen and hear nothing, the silence is also significant. It might mean that civilizations are rare or short-lived, or that they choose not to broadcast, or that our methods are inadequate. Silence could inspire introspection about our future and the fragility of intelligence. It could prompt us to protect our planet and to sustain our civilization so that we might one day reach out. The search is thus not only about them, but also about us. It reveals our desires, fears, and hopes, and it challenges us to think about what we value and what we want to become. As technology advances, new instruments expand the search. Radio arrays such as the Square Kilometre Array will be sensitive enough to detect Earth-level radio leakage from nearby stars. Optical SETI experiments look for nanosecond laser pulses. Space telescopes like the James Webb and future observatories will analyze exoplanet atmospheres for biosignatures. Artificial intelligence can sift through enormous datasets to identify patterns that human eyes might miss. The search is becoming more sophisticated, drawing on disciplines from computer science to anthropology. Each improvement tightens the constraints on the factors in the Drake equation, narrowing the range of possibilities. While we focus on our galaxy, there are hundreds of billions of other galaxies in the observable universe. Each contains millions or billions of stars and the potential for life, yet cosmic expansion and the finite speed of light limit our interactions. Even if civilizations exist in distant galaxies, signals may not reach us before cosmic acceleration carries them beyond our horizon. For practical purposes, we focus on our own cosmic neighborhood. The Milky Way, large though it is a manageable scale for communication within tens of thousands of light years. The finite speed of light makes conversation slow, but not impossible. A round trip to a civilization 100 light years away would take 2 centuries. Among the factors that shape N, human behavior influences F, sub C, and L. The choice to invest in science, education, and sustainability can prolong civilization. The decision to explore beyond our planet can protect us from planetary threats and provide new perspectives. By acknowledging our vulnerability and our potential, we can shape our own term in the equation. The Drake equation thus becomes not only a tool for estimation, but also a mirror that reflects our priorities. It invites us to imagine the future we want and to work toward it. The search for life and intelligence is a collective effort. Astronomers, biologists, chemists, philosophers, engineers, and artists all contribute. Some study the spectra of distant worlds. Others design instruments. Still others consider the societal implications. The interplay of disciplines mirrors the multiplicative nature of the equation. Progress in one area amplifies progress in others. The Green Bank meeting embodied this interdisciplinarity, and modern astrobiology continues it. Conferences and collaborations bring together experts to share data and ideas, to refine models, and to inspire the next generation. The question of cosmic companionship transcends borders and fields. At the level of individuals, the night sky continues to evoke wonder. Children gaze at the stars and ask whether anyone is looking back. Adults seek meaning and connection in the cosmos. Artists paint nebulae and comets. Writers conjure stories of alien worlds. Musicians compose symphonies inspired by the planets. The emotional response to the universe fuels curiosity and motivates science. It reminds us that the Drake equation is not just a formula. It is a story about our relationship with the cosmos. It provides a framework for turning awe into inquiry, for grounding imagination in data while preserving the mystery. In the centuries before telescopes, people built myths to explain the stars. They saw gods and heroes, dragons and rabbits. These stories were true in the sense that they expressed human values and fears. Today, we build scientific models, which are true in the sense that they describe and predict physical phenomena. Both forms of truth serve different purposes, and both are part of our engagement with the sky. The Drake equation sits at the boundary between myth and measurement. It takes the mythic question, "Are we alone?" and translates it into a set of measurable factors, each a story about stars, planets, life, minds, and time. Understanding these factors requires us to probe deeper into each domain. In astrophysics, we refine models of star formation and galactic structure. Simulations track how gas collapses, how turbulence and magnetic fields affect fragment sizes, and how feedback from young stars regulates further star birth. Observations with infrared and radio telescopes reveal star-forming regions hidden by dust. By comparing galaxies across cosmic time, we trace how star formation rates change and how galaxies evolve from chaotic clumps to organized spirals. These insights inform our estimate of our star, the birth rate of potential suns. In planetary science, we study protoplanetary disks around young stars. Observations with instruments like the Atacama Large Millimeter/Submillimeter Array reveal gaps and rings in these disks, evidence of planet formation in action. Models show how tiny dust grains stick together, form pebbles, grow into planetesimals, and eventually become planets. The migration of planets within disks can shape the architectures of planetary systems. By analyzing the diversity of known exoplanets, we learn which types of stars produce rocky planets, how common Earth-sized planets are, and how many might retain their atmospheres over billions of years. In the realm of biology, we investigate the origin of life. Laboratory experiments explore prebiotic chemistry under various conditions. In reducing atmospheres, in icy simulations of Europa, in high-pressure environments akin to deep-sea vents. Researchers study RNA molecules that can catalyze their own replication, supporting the RNA world hypothesis. Others examine metabolic cycles that could emerge spontaneously. Fieldwork examines extremophiles that thrive in hot springs, acidic lakes, and deep subsurface rocks, expanding our understanding of life's adaptability. These studies inform our sense of how easily life might arise, influencing F sub L. Within evolutionary biology, we investigate the emergence of intelligence. Comparative studies look at cognitive capabilities across species. Neuroscientists explore the physical basis of cognition and the evolutionary pressures that favor complexity. Anthropologists study human evolution, noting the role of cooperation, tool use, and language. Cognitive scientists consider whether intelligence can evolve in radically different forms, such as distributed intelligence in superorganisms or artificial intelligence. These perspectives inform F sub I and F sub C, reminding us that intelligence and communication may take many forms. Sociology and anthropology bring insight into the longevity of civilizations. They examine how societies respond to resource limits, conflict, and environmental change. Historians look at civilizations that have risen and fallen, drawing lessons about resilience and collapse. Economists study growth and sustainability, while political scientists analyze governance systems that can manage common goods. These social sciences inform L, the longevity term. They remind us that intelligence is only part of survival. Cooperation, adaptability, and foresight are equally important. In addition to science, the arts play a role in shaping our cosmic vision. Science fiction imagines possibilities beyond current knowledge, inspiring scientists and engineers. Literature explores ethical dilemmas associated with contact, such as the effect on cultures and identities. Visual arts depict alien landscapes and cosmic vistas, making abstract ideas tangible. Music expresses the emotional dimension of the search. These artistic expressions keep the question of life in the cosmos alive in public consciousness, ensuring support for research and fostering a sense of shared destiny. As we consider the factors in the equation, we must also acknowledge our limitations. Many of our estimates are bounded only by the fact that they lie between 0 and 1. The ranges span orders of magnitude. Yet even if we cannot assign precise numbers, the equation guides us to collect the relevant data. It encourages the design of missions to observe exoplanet atmospheres, to study star-forming regions, to search for technosignatures. It reminds us that the absence of evidence is not evidence of absence, and that patience is essential in cosmic-scale investigations. The values of the equation's factors are not constants. They evolve with time and knowledge. 50 years ago, F sub P was unknown. Now it is near 1. 50 years from now, we may know F sub L if we detect life on Mars, Europa, or an exoplanet. Discovery of intelligent signals could constrain F sub I and F sub C. Conversely, a long silence might suggest these factors are small, but it would not prove it. Science progresses by eliminating possibilities and narrowing ranges, not by confirming singular values in isolation. When we look up at the Milky Way, we see a ribbon of light composed of billions of unresolved stars. In reality, each star is a potential sun with its own family of planets. Some may have bright blue skies and red sunsets. Others might be enveloped in orange smog or covered in global oceans. On some worlds, life might barely cling to existence in subsurface niches. On others, forests of towering microbes could convert methane into energy. On still others, technological civilizations might harness energy from their stars with vast arrays, or they might retreat underground to avoid storms and flares. The variety of possible worlds stretches imagination. Contemplating this variety, we return to the question that ancient stargazers whispered: are we alone? The Drake equation does not answer the question, but it structures our contemplation. It connects myths to measurements, poetry to probability. It invites us to ask how common life and intelligence might be, what factors influence their emergence, and how our actions shape our future. Each term in the equation holds a story about stars, planets, life, minds, communication, and time. Each story is a research program and a philosophical inquiry. The equation also teaches us about humility. Our planet is one among billions in our galaxy, which is one among trillions in the observable universe. Our existence is both precious and not at all central. Recognizing this can inspire stewardship of Earth and respect for the possibility of other life. It can encourage global cooperation, because our shared fate is tied to the health of our planet and the longevity of our civilization. In this sense, the Drake equation is not only about others, it is about us, our values, and our future. As we near the end of our first exploration, the quiet question that has echoed since antiquity reverberates more deeply. The sky is still full of mysteries, but we now have tools to explore them. We have broken the question of cosmic companionship into parts and begun to investigate each one. We have recognized the interplay of astrophysics, chemistry, biology, evolution, culture, and time. And we have acknowledged the vast uncertainties and the need for patience and humility. With gentle curiosity, we will move forward, carrying the quiet question that has echoed since antiquity. The scene is Earth, some 4 billion years ago. The planet is young and restless, its surface dominated by raw oceans and volcanic landscapes. Lightning forks across a sky thick with storm clouds and noxious gases. Each bolt illuminates towering plumes of steam that rise from boiling pools. In this primeval darkness and chaos, something quietly profound is taking shape beneath the waters. At first glance, nothing about this world seems alive. Scalding rain pours into hot seas under an orange-tinted sky, filled with methane and ammonia. Yet the very violence of these conditions is forging new compounds. Energy from lightning and ultraviolet sunlight drives chemical reactions among the simple gases and water. In the depths of the ocean and in shallow ponds along rocky shores, molecules are colliding and combining in countless random dances. Over time, the sterile water becomes a broth of organic molecules, a primordial soup enriched by carbon and nitrogen compounds. Some of these ingredients may have formed on Earth itself, sparked by the planet's heat and electrical storms. Others arrive from space, riding in on meteorites and comet dust that rain down onto the early Earth. In this young solar system, collisions are frequent, and each impact can deliver more complex carbon-bearing molecules. The building blocks of life are accumulating everywhere, dissolved in the sea and spread across the wet clay of tidal flats. Deep below the waves, at cracks in the seafloor, another crucible of creation is at work. Here, superheated water, rich in minerals, gushes up from Earth's interior, the first hydrothermal vents. Around these vents, the ocean is a strange mix of extremes. Scalding fluids meet icy seawater, creating chemical-rich gradients and warm pockets. Within these pockets, simple molecules may find surfaces to cling to, like mineral chimneys made of sulfides. These natural chimneys act like laboratory beakers, concentrating chemicals and catalyzing reactions. In the dark ocean depths, far from sunlight, these places glow with the heat of the Earth and brim with reactive substances. They offer a sheltered haven where delicate chemical experiments can persist despite the world's surface chaos. From the shallows to the deep sea, many pathways toward complexity begin to unfold. Simple organic molecules link together into larger ones. Fragile chains of amino acids form fleetingly and sometimes break apart, but occasionally they persist. Fatty molecules, with one end repelled by water and the other attracted to it, naturally assemble into tiny spheres, forming the first membranous bubbles. These microscopic bubbles, or protocells, drift in the currents. They have no life, not yet, but they provide little pockets where chemicals can concentrate and react more efficiently than in the open water. Perhaps along a sunlit shoreline, waves splash a mixture of amino acids and other organics onto warm rocks. As the water evaporates under the weak young sun, the molecules left behind grow more concentrated. In these brief, drying moments, some of them bond together, forming longer chains. Then the tide comes in again, replenishing the pond and starting the cycle anew. Wetting and drying, heating and cooling, the environment swings through natural rhythms that may help simple molecules assemble into complex ones. In other places, lightning strikes a pond rich in dissolved gases, creating a spark of chemical change. Each flash synthesizes new organic compounds, which accumulate over years and centuries. Meanwhile, in the ocean, the constant flow of thermal energy at the vents drives its own cycles. Hot, mineral-laden water mixing with cooler water creates fluctuations in temperature and chemistry. These fluctuations might encourage certain reactions to happen repeatedly, slowly inching molecules toward greater complexity. One of the most intriguing steps on this journey is the formation of molecules that can make copies of themselves. Before true life can begin, there must be some form of molecular memory, a way to preserve improvements and innovations. Scientists suspect that long before DNA, a simpler genetic molecule took on this role. Perhaps it was RNA or something similar, a strand that not only carried information, but could also fold into shapes that sped up chemical reactions. In the warm soup of the early oceans, strands of primitive RNA might have assembled from smaller pieces. By pure chance, one strand may have helped create more of itself, acting as a catalyst. Those that replicated best would naturally become more common in the mixture. Imagine a tiny, rudimentary RNA-like molecule trapped inside a fatty bubble. When that bubble happens to split into two, it sometimes passes a copy of the molecule into each daughter bubble. Now there are two protocells where before there was one. In each, the cycle continues, molecules duplicating and vesicles dividing in a mindless but determined pattern. It is not yet life as we know it, but it is a crucial rehearsal for life's origin. A simple system capable of growth, variation, and chemical inheritance is coming into being. Over countless cycles and iterations, these molecular experiments grow more elaborate. Networks of reactions develop, where one product becomes the ingredient for another reaction, creating a self-sustaining loop. Some protocells contain mixtures that happen upon especially robust cycles, allowing them to grow and split more frequently. Each new generation of protocells can be slightly different from the last, as tiny changes occur in their chemical makeup. Natural selection, a concept that will drive evolution later, may already be at work on the molecular scale, favoring those chemical systems that are more stable or efficient in their environment. Time flows on, measured not in days or years, but in millions of years of slow chemical trial and error. The ocean is no longer a mere chemical broth. It is a dynamic landscape of countless microscopic reactions. The air above still knows nothing of life. There is no oxygen yet, no green of algae, only barren rock and water under the alien sky. But in the hidden crevices of the ocean floor, and in the gentle lapping of tidal pools, the precursors of living cells are assembling. Membranes, metabolic reactions, and genetic molecules are coalescing into more organized structures. At last, Somewhere in this world of chemical possibilities, the threshold is crossed. A protocell becomes a true cell, capable of both reproducing and carrying a simple code that guides its functions. Perhaps it happens in a clay-rich lagoon or next to a smoky undersea vent. We do not know exactly when or where, but we know that by around 4 billion years ago, Earth's first living organisms had emerged. They were likely nothing more than tiny bacteria-like cells feeding on the chemical energy around them. Yet they carried the spark of life, something entirely new in a previously lifeless cosmos. The first spark of life on Earth was not a sudden dramatic event, but a gradual dawn. By the time it fully ignites, the world has changed subtly. The oceans now host populations of microbes, invisible to the naked eye, but immensely consequential. These primitive life forms begin consuming simple nutrients and producing new substances as waste. In doing so, they initiate the earliest cycles of biology on the planet. The line between chemistry and biology has blurred and then vanished. Molecules have organized into a living system. This moment, when chemistry becomes biology, defines the quantity Fl in the Drake equation. It is the fraction of suitable planets where life actually takes hold. On Earth, that fraction became 1. Our planet had the right conditions, and life arose. But what about other worlds? As Earth's first microbes start multiplying, we turn our attention outward to consider how unique or common this spark might be. The journey from simple chemistry to living cell has succeeded here, under ideal circumstances. Now, we seek to understand the windows of opportunity that made it possible, and whether those windows might open on other planets as well. In the tumultuous youth of Earth, a fragile stability emerged. As the era of constant bombardment waned and the planet's surface cooled, water vapor condensed into liquid seas. By around 4.3 billion years ago, Earth had oceans, a global expanse of water that would cradle the first life. These early oceans were hot and laced with dissolved chemicals, but they offered something invaluable: continuity. For the first time, conditions remained wet and moderate enough for delicate organic processes to persist, instead of being obliterated by the next cataclysm. The stage was set, and time became an ally, rather than an enemy. Liquid water is key to life, and Earth managed to keep its oceans against the odds. The young sun shone dimmer than today, which could have left Earth frozen solid, yet it did not. Thick layers of carbon dioxide and other greenhouse gases blanketed the planet, trapping heat and keeping the oceans liquid under a faint sun. The atmosphere was mostly carbon dioxide and nitrogen, creating a warm, dense greenhouse that offset the sun's weakness. The sky might have been a hazy orange from all the mist and gases, but beneath it, the water stayed liquid. This fortunate balance solved the faint young sun paradox. Even with a cooler sun, Earth's surface stayed warm enough for life's chemistry to proceed. How did Earth maintain such balance for thousands of millennia? The answer lies in the planet's own regulatory cycles, natural feedback systems that acted like a thermostat. Volcanoes were one crucial player. Early Earth was highly geologically active, with volcanoes constantly erupting and spewing carbon dioxide into the atmosphere. This volcanic carbon dioxide built up the greenhouse effect, warming the planet. But as Earth warmed and rains fell, another process took hold: weathering. Rainwater, slightly acidic from dissolved CO2, washed over rocks and pulled minerals and carbon into rivers and eventually into the oceans. There, carbon could settle into sediments, locking away that greenhouse gas as carbonate rocks. In cooler times, this weathering slowed down, and CO2 from volcanoes accumulated freely until it warmed the planet again. In warmer times, weathering sped up and removed more carbon dioxide, preventing runaway heating. Over millions of years, this carbon-silicate cycle acted as a planetary heartbeat, gently pulsing the climate back toward equilibrium whenever it strayed. The result of these geochemical checks and balances was a remarkable long-term stability of temperature. Earth never became a lifeless snowball for long, nor did it boil its oceans away. There were fluctuations, periods of warmth, and even global glaciations. But life always found refuges, and the climate eventually returned to moderate ranges. These fluctuations themselves often triggered the feedbacks that restored balance. For instance, if ice advanced and covered much of the world, volcanic CO2 would accumulate since cold halted the weathering process. Slowly, the planet would warm again, melting the ice. On the other hand, if temperatures climbed too high, enhanced rainfall and weathering would draw down CO2, curbing the heat. It was a slow, natural seesaw that kept Earth's environment hospitable over eons. Beyond temperature, other planetary cycles also contributed to making Earth a comfortable cradle for life. The water cycle began churning early. Water evaporated from the warm seas, formed clouds, and fell back as rain. This continuous cycling of water helped distribute heat around the globe and provided fresh water and nutrients across the planet's surface. Each raindrop that fell carried minerals from land to sea, feeding the chemical soup in which life was budding. Meanwhile, deep within Earth, a churning metallic core generated a magnetic field that enveloped the planet. This magnetic shield deflected the harsh solar wind, streams of charged particles from the sun that can strip away atmospheres. Thanks to this invisible protective bubble, Earth's precious air and water were largely retained, unlike on some less fortunate worlds. We can imagine solar storms raging against Earth's magnetosphere, while below the oceans roll on, untouched and secure. The presence of our large moon also played a subtle but important role. The moon's gravity tugged at those early oceans, creating tides that washed the shorelines in a steady rhythm. Every high tide was like a global pulse, stirring coastal waters and perhaps concentrating organic molecules in tidal pools, then stranding them on land as the tide receded. This daily mixing could have accelerated some prebiotic chemical cycles. Additionally, the moon helped stabilize Earth's axial tilt, the angle at which our world leans as it orbits the sun. Because of this stabilization, Earth experienced regular seasons instead of wild swings in climate. The seasons on the early Earth were gentler than they might otherwise have been, giving nascent life a consistent and predictable cycle of warmer and cooler periods each year, rather than chaotic climate lurches. A stable tilt meant no extreme ice ages triggered by a random wobble, and no boiling summers alternating with frigid winters. The climate rhythms were moderate and life-friendly. Day and night cycles also rolled endlessly on, as Earth spun faster than it does now. A day might have been only a dozen hours long in the distant past. This rapid day-night cycling meant the planet's surface alternately warmed and cooled in quick succession. Such cycles prevented any one part of the surface from overheating under continuous sunlight. They also introduced a natural tempo to any photochemical processes. Early microbes, once they existed, would eventually take advantage of daylight for energy and then rest during darkness. Even before life, some chemical reactions may have proceeded only under sunlight and paused at night, adding yet another oscillation that could influence chemical evolution. All these planetary rhythms, the carbon cycle, the water cycle, tides, day-night, seasons, were like the rocking of a cradle in which life could gently fall asleep and awaken again and again in safety. Earth's geology and astronomy conspired to create windows of opportunity, periods when conditions were just stable enough for life's first fragile steps. It is unlikely to be a coincidence that life emerged during a relative calm, following the violent early era. With the heavy asteroids no longer pounding constantly and the oceans established, Earth entered a golden window where the chemistry sparked in the first chapter had time to flourish and organize into biology. Once life began, it started to interact with these cycles, weaving itself into the planetary balance. Early life forms consumed chemicals like hydrogen and carbon dioxide and released methane, a potent greenhouse gas. This methane may have supplemented the warming at a time when the sun was still dim, further stabilizing Earth's climate. In this way, life itself quickly became part of Earth's feedback mechanisms, helping to keep the environment habitable for more life. There was a partnership between the living and non-living Earth, even from the start. Geology set the initial rules, and biology soon joined the dance. Through all these cooperative cycles and stabilizing feedbacks, Earth avoided catastrophes that could have snuffed out nascent life. The planet had just enough of everything in the right proportions: a protective magnetic field, a large moon, flowing water, active geology, to navigate the narrow path between freezing and boiling, between chaos and stagnation. This delicate balance lasted not just for a moment, but for billions of years, giving life the continuity it needed to progress from simple cells to the complex biosphere we know today. In cosmic terms, Earth's sustained habitability is an exceptional stroke of luck, or perhaps a blueprint for how a life-bearing world operates. As we contemplate this window of opportunity that allowed life to thrive here, a question arises. Could other worlds have enjoyed similar windows? Could they too have the right balance of cycles and feedbacks to keep an environment hospitable long enough for life to spark and persist? Our gaze shifts outward again, to the many different kinds of planets and moons beyond Earth. Some of them had oceans once, or still do. Some have the right size and composition to hold an atmosphere and regulate a climate. Are there other cradles rocking in the vastness of space, protecting their own embryonic lives? With Earth's success in mind, we begin to explore the many kinds of homes that might host life across the solar system and beyond. Mars is our neighboring world, and one of the first places we look when imagining another home for life. Today, the red planet is cold, dry, and quiet, a desert of rust-colored dust under a thin sky. But long ago, Mars was more Earth-like. Ancient riverbeds scar its surface, winding and branching as though carved by flowing water ages past. Rovers have found telltale signs of clay and minerals that only form in liquid water, confirming that Mars once had lakes and maybe even a vast northern ocean. We can picture that young Mars, volcanoes rumbling in the distance, rivers coursing through valleys, perhaps a blue sky tinged with pink at sunset, and crater lakes reflecting sunlight. During that epoch, billions of years ago, Mars had the key ingredients: water, warmth, and time to potentially nurture life's spark. If life ever took hold on Mars, it might have been simple and microbial, hiding in the shallows of lakes or clinging to hydrothermal springs. Mars's window of habitability was not open for long. Over time, the planet's internal dynamo faded, and it lost its global magnetic field. With little magnetic protection, the solar wind began stripping Mars's atmosphere. The once thick air thinned, the pressure dropped, and water on the surface either froze or evaporated into space. Lakes and rivers vanished, leaving only their ghostly traces. If Martian life began, it may have faced a fight against a world growing ever more inhospitable. Perhaps some hardy microbes retreated underground as the surface froze, finding refuge in pockets of briny water or deep aquifers warmed by the planet's heat. Even now, Mars teases us with hints: occasional methane gas spikes in its atmosphere, that some speculate could be burps of microbial activity below ground. Though these signals could also be geological, they keep alive the hope that Mars is not completely dead. Our explorations of Mars serve as a lesson in planetary chance. Two worlds, Earth and Mars, started with similar promise: water, organic molecules, sunlight. On Earth, life blossomed. On Mars, we are still searching for any sign that life even flickered. Mars became a laboratory that ran the experiment and perhaps aborted it early. Today, robotic rovers trundle across its plains, drilling into rocks that might harbour fossilized microbes from a wetter age. Every grain of clay or whiff of organics, they find whispers of a time when Mars could have been alive. If we discover that life arose there too, even if only briefly, it would mean the cosmic dice rolled life on two adjacent planets. A strong hint that life might be common. If, on the other hand, Mars never birthed life despite favourable beginnings, we must wonder what subtle requirement was missing, or what catastrophe intervened. Either outcome teaches us more about FL, the fraction of worlds that develop life. Beyond Mars, the outer solar system presents entirely different kinds of habitats. Places that seemed unlikely at first, but now look surprisingly promising. Chief among them are the icy moons orbiting the giant planets. Take Europa, a moon of Jupiter, roughly the size of our moon. Europa's surface is a shell of ice crisscrossed by reddish-brown cracks. It looks like a frozen sea that someone has shattered and clumsily patched back together. Beneath that cracked ice, astronomers are confident an ocean of liquid water swirls. Europa is warmed not by sunlight. It's far from the sun and locked in an endless icy night beneath Jupiter's shadow, but by the tug-of-war gravity of Jupiter and its other moons. This tidal heating flexes Europa's interior, keeping its ocean from freezing solid. In that dark ocean, there may be hydrothermal vents on the seafloor, akin to those on early Earth, pumping mineral-rich warmth into the water. All the ingredients we think necessary for life, water, energy, and chemistry, exist in Europa's hidden realm. We cannot see it directly, but sometimes geysers of water burst through cracks and erupt into space, as captured by passing spacecraft. In those brief fountains, we have detected hints of salts and even simple organic molecules. It is as if Europa is offering us tiny samples of its ocean, teasing that it could be a living ocean, home to microbes or something even more complex. Another tiny world, Enceladus, orbits Saturn and has captured scientists' imaginations in a similar way. Enceladus is a small moon, just about 500 kilometers across, yet it hosts a subsurface ocean beneath its bright ice. We know this because Enceladus dramatically vents its ocean into space through huge plumes erupting from cracks near its south pole. When the Cassini spacecraft flew through those plumes, it tasted the moon's inner secrets: water vapor, a variety of organic compounds, and microscopic grains of rock that hinted at hot water interacting with rock at the ocean bottom. Crucially, Cassini also found molecular hydrogen in the plume, a telltale sign that hydrothermal vents likely exist on Enceladus's seafloor, producing hydrogen by reacting with rocks. On Earth, similar vents teem with microbial life that feed on chemical energy. Enceladus, then, has a potentially habitable ocean about the size of Lake Superior, kept liquid by Saturn's gravitational kneading and offering chemical energy in its depths. It is a pristine laboratory, a miniature ocean world where life could independently arise or perhaps even still thrive in the dark. And then there is Titan, Saturn's largest moon, which presents a completely different kind of environment, one that challenges our Earth-centric notions of habitability. Titan is often likened to an analogue of early Earth, with a thick atmosphere mostly of nitrogen and a rich organic chemistry. Standing on Titan's surface, were we able to, one would see a dim orange haze filtering a feeble sun. The air pressure is higher than Earth's, and strangely, it rains. Not water, but liquid methane. Titan's surface hosts rivers, lakes, and seas of methane and ethane, hydrocarbons that are gases on Earth, but liquid in Titan's frigid cold of -179 degrees Fahrenheit, degrees Celsius. Water there is locked up as rock-hard ice, a permanent bedrock beneath the hydrocarbon pools. It's an alien scene. Dunes of organic smog particles, lakes that reflect Saturn's distant glow, and perhaps drizzle of liquid methane from slow-moving clouds. Could life exist in such a place? It would have to be very different from life on Earth, potentially using liquid methane as a solvent instead of water, and chemistry that operates at a crawl in the cold. Some scientists have speculated about exotic biochemistries, maybe microbes that breathe hydrogen and exhale methane, swimming in Titan's liquid lakes. No direct evidence exists yet for life on Titan, but intriguingly, we have detected complex organic molecules in its atmosphere and on its surface. Titan's chemistry is a rich stew that nature has been simmering for eons. Whether it has cooked up something alive remains one of the great unanswered questions. Interestingly, Titan is a double laboratory. Not only does it have those surface lakes of methane, it also conceals a water ocean deep beneath its icy crust, just like Europa and Enceladus. So Titan offers two starkly different potential habitats in one world. One unimaginably cold and hydrocarbon-rich at the surface, and one warm, by comparison, and wet beneath the ice. Life, if it exists there, could take completely different forms in each environment. Titan reminds us that habitable might not have a single definition. Nature could surprise us with life forms that use liquids and elements in ways we have yet to dream of. Beyond our solar system, the number of potential homes for life expands into the countless stars overhead. In the past 2 decades, astronomers have discovered thousands of exoplanets orbiting other suns, and among them, many that appear to be temperate and could host liquid water. These temperate exoplanets come in an astonishing variety. Some are rocky planets, only slightly larger than Earth, circling in the so-called habitable zone of their star, the range of distances where a planet is neither too hot nor too cold for liquid water. Around dim red dwarf stars, the habitable zone hugs close to the star, meaning planets there might be tidally locked, one side always facing the star, the other in perpetual night. Even these worlds could be habitable, perhaps with a band of twilight where temperatures are just right, or with thick atmospheres that circulate warmth to the night side. Around sun-like stars, we have found planets like Kepler 452b, which is often nicknamed an older cousin of Earth, residing in a favorable orbit where oceans could exist. And then there is the intriguing TRAPPIST-1 system, a cool red star with 7 Earth-sized planets, at least 3 of which lie in the habitable zone. Imagine a sky where other inhabited worlds might be visible overhead as nearby siblings. TRAPPIST-1's tightly packed miniature solar system tempts the imagination in that way. Exoplanets also challenge what environments we consider life-friendly. We've found examples of worlds that might be entirely covered in water. Global oceans with no land at all, sometimes called water worlds. If life can arise in oceans without dry land, as it likely did on Earth originally, such planets could be tranquil marine biospheres beneath endless waves. Others might be desert worlds with oasis-like polar seas, or moons around giant planets that themselves provide warmth via tidal forces, just as Jupiter's moons do. Some of the temperate exoplanets we've detected have sizes between Earth and Neptune. These might have thick, hydrogen-rich atmospheres and deep layers of high-pressure water. Environments very different from Earth's surface, but possibly stable and warm deep inside. We simply don't know yet, but the diversity of planets is teaching us that what counts as a potential cradle for life is broader than we imagined. With each new exoplanet discovery, we realize our solar system's examples: an Earth here, a Mars there, some icy moons, are just a few cases in a vast cosmic gallery. There may be planets with twin suns, planets with rings and dozens of moons, planets that orbit ancient red stars where life had billions of extra years to evolve, or young planets still cooling. Life could start in any of these, given a niche of stability and the right chemistry. In some cases, nature might run experiments we haven't even considered. Life in clouds, life in ice, life in exotic chemical soups. For now, we focus on the familiar signposts, liquid water being the foremost, because that's what we know worked here. It serves as a guide to identify the most promising homes out there. In our galaxy alone, there are likely billions of planets in habitable zones. Not all will be comfortable. Some might be on the edge of too cold or too hot. Some may have thin atmospheres like Mars, or overly thick ones like Venus. But even if a small fraction are truly Earth-like, that's still millions of worlds, potentially bearing the conditions we think are needed for life. Each of those worlds is like a dice roll for life's emergence, a separate laboratory where the experiment of abiogenesis could succeed or fail. The Drake equation's term for these environments, NE, the number of habitable planets per star, hints at the vast number of chances. But FL, the fraction where life actually begins, is the outcome of those experiments, and it might differ on each world. Standing on Earth under the night sky, we can point to the faint glimmer of exoplanets by the data we've gathered, but we have yet to confirm life anywhere else. Still, as we line up these many candidates, Mars, Europa, Enceladus, Titan, distant exoplanets like those of TRAPPIST-1 or Kepler, one cannot help but wonder if life might have begun in one or several of them. Perhaps microbial ecosystems lurk beneath the European ice, or fossil remnants lie entombed in Martian rock. Perhaps on a planet orbiting a nearby star, forests wave in alien winds, or strange creatures swim in dark alien seas. These possibilities inspire our search and animate our science fiction, but they also ground us in a sobering reality. Until now, Earth is the only confirmed life-bearing world. All these diverse homes could have harbored their own biospheres, yet we have not seen obvious evidence of life beyond our planet. It could be that our techniques are not yet sensitive enough, or simply that we haven't looked in the right way. Or it could be that some hidden hurdles have kept these worlds sterile despite favourable conditions. This brings us to an important consideration. Even with the right home, life's spark might be fragile. What challenges or catastrophes might snuff out life's chances on an otherwise promising world? As we turn to the next part of our journey, we will examine the stumbling blocks and bottlenecks, the perils that can befall a young planet or its budding life, potentially explaining why some inviting abodes remain lifeless despite all their apparent promise. Even on a welcoming world, fate can intervene cruelly. A planet might have all the right ingredients for life, only to suffer a catastrophe that resets the clock to zero. One of the most fearsome dangers comes from above, the impact of a large asteroid or comet. In the early days of any planetary system, collisions are common. We picture a nascent biosphere, tiny microbes just beginning to populate a warm ocean, when suddenly a mountain-sized rock tumbles from space. The impact is unimaginable. Releasing energy rivaling millions of nuclear bombs, it can ignite global wildfires and throw so much debris into the sky that the sun is blotted out. If the object is big enough, the shock can boil away entire oceans in a day, enveloping the planet in scalding steam. Any fragile life in its vicinity would be extinguished instantly, and even life far from the impact might not survive the aftermath of darkness and acid rain. Early Earth likely endured many such sterilizing impacts during the heavy bombardment phase. Perhaps life arose and was wiped out more than once before the bombardment ceased. We have evidence that Earth's last giant life-threatening impacts ended around 3.9 billion years ago, just before our earliest signs of life appear. It could be that only once the cosmic crossfire calmed could life truly gain a permanent foothold. A less fortunate planet, pelted a little longer or hit by one extra-large asteroid at the wrong time, might never get the chance to nurture life beyond a few false starts. But violence from space is just one hazard. A planet's own atmosphere and climate can turn against life as well. Consider Venus, often called Earth's sister due to its similar size and composition. By rights, Venus might have been a lush twin of Earth, but it became a cautionary tale of climate gone awry. If life ever had a chance there, it was scotched by a runaway greenhouse effect. Being slightly closer to the sun, Venus received more sunlight. Water that might have once pooled on its surface evaporated into the air. Water vapor is a potent greenhouse gas, trapping heat, which caused Venus to warm further. In a vicious cycle, the oceans, if they existed, would have boiled away completely. Without water to absorb carbon dioxide and lock it in rocks, CO2 accumulated to extreme levels in the atmosphere. The result is the Venus we know today. A crushing atmosphere 90 times heavier than Earth's, composed almost entirely of carbon dioxide, with clouds of sulfuric acid and surface temperatures hot enough to melt lead. Any organic molecules or nascent life would have been obliterated in that pressure cooker. Venus shows how a planet can slip from habitable to hellish if conditions tip beyond a critical point. In Drake equation terms, a world like Venus could have had Ne equals 1. It was in the Sun's habitable zone initially. But Fl equals 0, no life, because the environment deteriorated too quickly or too severely. At the opposite extreme, a planet might become a frozen snowball, presenting a different challenge to life. Earth itself experienced a few near-global glaciations, snowball Earth episodes, where ice reached from the poles toward the equator, turning the planet white and sunlight reflective. Yet Earth's robust carbon cycle eventually rescued it, as volcanic CO2 built up under the ice and triggered a thaw. On a smaller or less active planet, such a freeze might never end. Imagine a world slightly farther from its star than Earth, or with less volcanic output. Ice advances, temperatures plummet, oceans solidify into miles-thick glaciers, and the reflectivity of all that ice prevents the planet from ever warming again. Life that began in a temperate era could find itself confined to perhaps a few pockets of liquid water near geothermal springs, struggling to hang on. If those refuges freeze, it's extinction. Even if a snowball planet isn't completely dead, any life is likely minimal and trapped, unlikely to thrive or evolve further. Without a friendly climate, Fl for that world could stagnate at a tiny value. Life either never advances beyond a marginal presence or disappears entirely. Another silent killer for a budding biosphere is the loss of a planet's atmosphere and water, the drying out that turned Mars into the barren world we see. As we saw with Mars, size and magnetic field matter enormously. A planet that is too small may not hold on to its internal heat for long. When its core cools and solidifies, as happened on Mars, the magnetic field fades away. At that point, the planet's atmosphere stands naked against the stellar wind, that continuous stream of high-energy particles from the star. Over time, the wind erodes the air, stripping lighter molecules into space. The air thins, the pressure drops, and any surface water either sublimates into vapor and escapes or freezes out. A once wet planet contracts into an icy desert. For Mars, this meant the end of rivers and lakes, and any surface-dwelling life would have perished or been forced underground. It's a sobering thought. A world can have life-friendly conditions for hundreds of millions of years, and then gradually slip out of the habitable zone, not by moving farther from the sun, but by effectively losing its protective blanket of air and water. Even a planet as large as Earth could suffer atmospheric loss under certain conditions. If Earth were orbiting a very active star, say a red dwarf with frequent powerful flares and coronal mass ejections, those blasts of radiation could chew away at our atmosphere, especially the ozone layer, exposing any surface life to harmful ultraviolet rays. Repeated flares could erode the atmosphere itself if the planet's magnetic shield wasn't strong. Many exoplanets in tight orbits around their stars face this kind of trial by fire. For instance, planets around red dwarfs may be so close to their star to stay warm that they endure intense X-ray and UV radiation. Some may start with thick atmospheres that then get eroded over a few billion years. A world could begin its life with oceans and rich air, only to be slowly desiccated. By the time we might observe it, the seas could be gone, and only a thin, inhospitable atmosphere remains. A failed garden where life either never took hold or was wiped out as conditions worsened. Beyond these major threats, impacts, climate catastrophe, and atmospheric loss, lie more subtle bottlenecks that can limit life's progress. A planet might have life emerge, but environmental hurdles could keep it from diversifying. Imagine a biosphere that remains confined to hot spring oases because the rest of the planet is too cold or too dry. Or a planet where life thrives for a time. Then a change, like volcanic supereruptions or a nearby gamma ray burst from a dying star, delivers a blow that extinguishes it after millions of years of effort. Life might not rebound as it did after Earth's mass extinctions if the event is too severe or the environment too marginal to begin with. There's also the matter of time. Stars change over time, and some planets may have a narrow window before conditions degrade. For example, if a star grows hotter or more luminous as it ages, as our Sun will, the habitable zone moves outward. A planet that was once perfectly situated could become too hot, and if life hasn't advanced to a resilient stage, it might not survive the transition. Earth will face this in the far future. Fortunately for us, the sun's warming is slow, but around smaller, quicker-burning stars, that window could be much shorter. All these stumbling blocks suggest that the value of FL, the chance life arises on a habitable planet, might be suppressed in many cases by planetary misfortune. The universe could be filled with worlds that were habitable in principle, yet lifeless in practice because something went wrong. Perhaps an asteroid always came when it shouldn't have, or the planet was just a bit too close to its star, or a protective magnetic field never kicked in. These are the tragedies of potential, gardens that never bloomed or wilted too soon. Yet it's important to note that life, once established, can be tenacious and resourceful. Earth's own history shows life enduring through massive impacts, volcanic winters, and ice ages. Microbes can lie dormant through hellish conditions and re-emerge when things improve, so even some stumbling blocks might not mean absolute extinction. Life could cling on in deep underground pockets or beneath ice, waiting out a disaster. This dogged resilience of life will be our focus shortly. But before we get there, we should consider how we might detect life's presence on other worlds in the first place, and how we might be fooled. After all, if many planets have flirted with life, or hold only sparse biospheres due to these challenges, how would we recognize that? The clues life leaves in atmospheres and on surfaces are delicate and can be mimicked by abiotic processes. Our search for extraterrestrial life therefore demands not just hope, but caution and discernment. We move on to examine those clues. the biosignatures, and their potential false positives, in our quest to know if we are truly alone or just one oasis among many. How would we recognize life on a faraway world? We cannot yet visit these planets in person, so we must rely on subtle clues, like detectives searching for fingerprints at a crime scene. The fingerprints of life are known as biosignatures, distinctive signs that living processes are at work. One of the most telling biosignatures is a curious mix of gases in a planet's atmosphere. Life has a way of pushing chemical balances out of equilibrium. Take Earth as an example. Our atmosphere contains a large amount of oxygen produced by photosynthetic organisms, and a steady trickle of methane from microbes and other sources. Oxygen and methane normally would react with each other, so having both exist together means something, in this case life, is constantly replenishing them. If we observed an exoplanet with a similar atmospheric imbalance, say lots of oxygen coexisting with methane or other reactive gases, it would be a strong hint that something analogous to biology is breathing and metabolizing there. Astronomers are learning to read these atmospheric clues by analyzing the faint starlight that filters through a planet's air when it passes in front of its star. From this, we can identify certain gases. Already, the Hubble and James Webb Space Telescopes have detected water vapor, and even molecules like carbon dioxide and methane in the atmospheres of some giant exoplanets. For smaller Earth-like planets, the task is harder, but within reach in the coming years. We dream of seeing an exoplanet's spectrum with unmistakable markers, perhaps the imprint of O2, alongside signs of water, and maybe a dash of methane or nitrous oxide, a gas released by life here. O2 alone would be intriguing. On Earth, virtually all our oxygen comes from life, plants, algae, and bacteria. But we must be cautious. It turns out there are ways to get oxygen without life. A planet orbiting a very active star, for example, might have its water vapor continuously split by intense ultraviolet radiation. The hydrogen escapes to space, and the oxygen is left behind, building up over time. Such a planet might have a sky full of O2, yet no organisms at all. A false positive for life. Therefore, context is everything. We'd look at the star's behavior, the planet's likely history, and search for additional corroborating gases. Oxygen, in combination with an unexpected partner, like methane, or large amounts of hydrogen, or even compounds like dimethyl sulfide if we were lucky enough to detect it, would strengthen the case that biology is involved. Apart from gases, life can reveal itself on a planet's surface through unusual colors or reflective properties. Our own Earth, when viewed from space, doesn't just appear as a blue marble. In the near infrared, it shows a peculiar red edge, a sharp change in reflectance caused by vegetation. Green plants absorb visible red light for photosynthesis, but reflect infrared light strongly, creating a spectral signature that is difficult to mimic with non-living matter. If someday we have telescopes powerful enough to pick out the light from an Earth-like exoplanet directly, we will be on the lookout for such a feature. A sudden jump in reflectivity at certain wavelengths could mean vast expanses of alien foliage or algae-like mats on the surface. However, even here we must be wary. Could something else imitate a vegetation signal? Perhaps extensive fields of a mineral with specific reflective qualities might coincidentally produce a similar pattern. It's unlikely to perfectly mimic the red edge, but scientists remain careful, devising multiple ways to confirm what they see. Then there are more fleeting biosignatures, seasonal changes in atmospheric disequilibria or in surface color. On Earth, for instance, CO2 levels drop in the northern hemisphere's summer as plants grow and consume the gas, then rise again in the winter when plants are dormant. An advanced telescope observing an exoplanet over many years might detect periodic oscillations in certain gas levels, or even slight shifts in the planet's color as forests leaf out or decay. These rhythmic patterns would be hard to explain without life. Imagine seeing a world where every year the spectrum shows a surge of oxygen and a reduction of CO2, like a planet breathing in and out. That would strongly hint at some global photosynthesis cycle. Still, one must check alternative explanations. Perhaps the planet has regular volcanic seasons or weather patterns that could cause similar gas fluctuations. Our own solar system provides cautionary tales about biosignature false alarms. We've observed methane on Mars, which on Earth often signifies life, from cow guts to swamp bacteria. But on Mars, it could also come from geological reactions. For example, water reacting with certain minerals underground can produce methane. Likewise, in recent years, scientists thought they found phosphine gas high in the clouds of Venus, a molecule that on Earth is associated with microbial life. This sparked excitement that something might be alive in Venus's temperate cloud decks. But follow-up studies cast doubt, suggesting the signal might have been an error, or that unknown chemistry could be producing phosphine without life. These episodes remind us how careful we must be in interpreting signals. A single interesting molecule is never absolute proof. It's the ensemble of evidence that matters. The concept of disequilibrium is often invoked as the golden standard for biosignature detection. Life constantly drives things away from chemical equilibrium. If we find a planet where the atmosphere is in an energetically uneasy state, like Earth's mix of oxygen, which likes to react, and methane, which would quickly react with oxygen, it suggests something is continually pumping it full of those gases against the natural tendency to neutralize. It's as if we opened a sealed jar and found it full of smoke and flame. We'd suspect something inside is actively burning. On a planetary scale, that burning or renewing of gases would be life, but we have to ensure it isn't a volcano or photochemical effect doing a similar job. For example, certain exoplanets might accumulate oxygen if they lose their oceans, as noted, or produce methane from intense geological activity. We have to examine all the clues in concert: the star type, the planet's temperature, whether there are signs of recent water, and multiple gases at once. Biosignatures are not limited to atmospheres. We also consider that life might alter its environment in other detectable ways. It could, for instance, color the surface with unusual pigments. Algal blooms can turn entire lakes green or red. Forests darken continents. Perhaps on another world, life forms could excrete reflective shells that change the glint of shorelines, or create vast colony structures, like coral reefs, that ever so slightly skew the planet's overall color. We have even entertained the idea of cities or nighttime lights as technosignatures, signs of intelligent life. But those belong to a later part of the Drake equation. For now, we focus on signs of simple life, and those signs can be whispers. We must be prepared to listen carefully. Adding to the challenge, there are also false negatives, cases where life might exist but give off little obvious signal. A planet covered by a thick ice layer could have a thriving ocean beneath, like Europa. But from the outside it looks inert, with no atmospheric hint of biology escaping through the ice. Or a world with life might have a very low-level equilibrium with its environment, producing gases that are quickly absorbed by the oceans or soil, so nothing accumulates to tell us from afar. Early Earth, for a couple of billion years, had life but no oxygen in the air. An alien astronomer observing Earth at that time might not have noticed a biosignature, despite an ocean full of microbes. This means that even if we don't detect obvious biosignatures on a promising planet, we cannot be entirely sure it's lifeless. It might just be quiet or hidden. Therefore, the search for biosignatures is a delicate art of inference. It requires ruling out non-biological sources for any signal we see, and ideally finding multiple lines of evidence that all point to life. It is a bit like diagnosing a patient. One symptom can mislead, but a whole suite of symptoms can give a clear diagnosis. Scientists talk about using biosignature suites, combinations of gases and perhaps surface features that collectively would be very unlikely without life. Despite the difficulties, this is an incredibly exciting endeavor. For the first time in history, we have the tools to probe other worlds for these hints. New observatories are being designed to peer at Earth-sized planets around nearby stars, splitting their faint light to look for those telltale chemical fingerprints. The moment we detect a strong biosignature, say a planet with oxygen, water vapor, and a dash of methane, or some other convincing combination, humanity will know that life is not unique to Earth. Until that day, we proceed with both eagerness and caution, aware that nature can trick us, but also mindful that life, if present, often finds a way to announce itself. Should we one day find a clear sign of life out there, it will tell us that the cosmic dice can come up life more than once. If we find ambiguous signs, we will keep refining our methods until we can be sure. And if, after thorough searching, we find nothing even on seemingly habitable planets, that will be equally profound. It would hint that life might be exceedingly rare or fleeting. Right now, we are on the cusp of these revelations. Our role is akin to distant observers, sniffing the breeze of alien worlds for an aroma of life. When we do detect life's traces, or if we do, we also have to consider what that life might be like and how hardy it is. A strong biosignature implies not just a spark of life, but a flame that has endured. How tough is life, and how far can it adapt to strange environments? The answer, hinted at by Earth's most extreme organisms, is far more than one might initially assume. Our exploration continues into the realm of life, at the extremes and the patterns evolution tends to follow, for clues about life's prevalence and persistence in the universe. On Earth, life has proven to be astonishingly tough and inventive. Once the spark of life ignited, it did not remain confined to the gentle cradle of a warm pond or a sunny ocean surface. Instead, it spread to every extreme corner of the planet, adapting to conditions that would seem utterly uninhabitable. This tenacity gives us confidence that if life arises on a world, it will fight hard to stay, and it will likely colonize every niche it can find. Consider the extremes of temperature. We find microbes called hyperthermophiles thriving in boiling hot springs and deep-sea hydrothermal vents at temperatures above 100 degrees Celsius, where water is scalding enough to cook any ordinary organism. Yet these heat-loving bacteria and archaea flourish. Their enzymes specially tuned to remain stable and active at temperatures that would destroy the proteins of most life. On the flip side, other microorganisms, psychrophiles, persist in permafrost and inside Antarctic ice, metabolizing slowly at temperatures well below the freezing point of water. Some have been resuscitated after being frozen for thousands of years, effectively enduring suspended animation in solid ice. If an alien world is a frozen snowball or a searing hydrothermal landscape, we know from Earth's playbook that life could still eke out an existence there, given the right adaptations. Acidity and toxicity do not stop life either. In sulfuric acid pools, with pH values at 0, as corrosive as battery acid, certain algae and bacteria manage to live. In the opposite extreme, extremely alkaline lakes still harbour specialized microbes. There are bacteria that breathe metals like iron or sulfur instead of oxygen, and others that can feast on what we consider poisons, converting toxic chemicals into food. Deep beneath the ground, miles below the surface, we have found microbes living in solid rock, feeding on trace energy from radioactive decay in the minerals. These endoliths may spend centuries in slow motion, dividing perhaps once in a few thousand years, yet they are alive and enduring in total darkness and isolation. Their presence hints that a seemingly barren planet could harbour a hidden biosphere deep underground, out of sight. One of the most dramatic demonstrations of life's resilience was the discovery of organisms that can withstand intense radiation. The bacterium Deinococcus radiodurans was nicknamed Conan the bacterium for its ability to survive doses of radiation that would obliterate human cells many times over. It stitches its DNA back together after it shatters, as if nothing happened. In the ruined nuclear reactor of Chernobyl, certain fungi actually thrive in high radiation, apparently using pigments to harvest energy from gamma rays, literally eating radiation the way plants use sunlight. This adaptability suggests that even worlds bathed in higher radiation than Earth might still foster life, perhaps underground, or shielded by rock or ice, emerging during quieter periods. If a planet loses its ozone layer and is bombarded by intense ultraviolet light, there might still be life in shaded nooks, caves, or under soil, waiting out the storm. Life's stubbornness extends even to the vacuum of space. Experiments have exposed bacterial spores and tiny animals called tardigrades to open space, the cold, airless void, for days, even weeks. Many survived the ordeal, reviving when returned to normal conditions. Tardigrades, in particular, have become famous for their near indestructibility. They can dry out into a husk and stay inert for years, then rehydrate and spring back to life as if nothing happened. They have survived not only space vacuum, but extreme pressures, high doses of radiation, and temperature swings from near absolute zero to above boiling. Such creatures underline that life can endure interplanetary journeys, encased in rocks blasted off one planet and landing on another. This raises the intriguing possibility that life could spread from one world to another, a concept known as panspermia. If a meteorite bearing microbes from an inhabited planet impacts a sterile one with suitable conditions, those hardy microbes might seed the new world. In our own solar system, we know meteorites have travelled between Mars and Earth. It's conceivable that if life existed on Mars early on, it could have hitchhiked to Earth or vice versa. The implication is profound. FL might not be entirely independent for each planet if life can propagate across space. A single origin of life could, in theory, populate multiple worlds in a system given time and opportunity. Another comforting pattern we observe in Earth's history is that life, once established, is incredibly persistent. Our planet has experienced at least 5 mass extinctions, catastrophic events that wiped out a majority of species each time. Yet in each case, a remnant of life always survived. Often the small, the burrowing, the microbial. And from those survivors, life rebounded, diversified, and filled the world anew with even greater variety. After the asteroid that ended the reign of the dinosaurs, mammals and birds proliferated. After ancient ice ages that nearly sterilized the seas, new types of algae and eventually complex animals emerged in the relatively empty world. This suggests that even if a planet faces periodic disasters, life might repeatedly recover and adapt as long as something survives. It would take an almost unbelievably thorough catastrophe to extinguish all life once a biosphere is widespread. Think of Earth during the worst extinction event, the Permian extinction. Over 90% of species died, yet the tree of life itself remained, and soon there were thriving ecosystems again. Life is, in that sense, ferociously clingy. It only needs a toehold to bounce back. The phenomenon of convergent evolution speaks to a certain predictability in life's solutions to environmental challenges. On Earth, different lineages in isolation have evolved remarkably similar traits. Eyes have evolved independently in various forms at least half a dozen times, each time permitting organisms to sense light and navigate their world. Flight evolved separately in insects, birds, pterosaurs, and bats, giving each the ability to explore the skies. Even at the microbial level, disparate bacteria have independently developed the same biochemical tricks to exploit sources of energy or resist stresses. This convergence suggests that on any world where life arises, evolution may be guided by the same physical and chemical realities to find analogous innovations. If there is light, organisms may evolve some way to sense it, perhaps eyes or photosynthetic pigments to use that light. If there is a fluid medium, water or another liquid, some life forms will evolve to swim, maybe with fin-like appendages or jet propulsion as squids have. If there are surfaces to crawl on, something like legs or slime-based gliding might appear. We can imagine alien worlds with creatures that have completely different ancestries from Earth's life, and yet fill similar ecological roles. Photosynthesizers, scavengers, predators, filter feeders, and so on, each shaped by convergence to the demands of physics and environment. This doesn't mean life elsewhere will mirror Earth's life exactly. Far from it, there will be wondrous differences, but the recurring themes might be familiar. Adaptability is perhaps life's greatest hallmark. When the environment changes, life responds, either by migrating, going dormant, or genetically adapting over generations. We have bacteria that can incorporate new genes from their surroundings to gain useful abilities, like digesting a novel compound when needed. We have insects and microscopic animals that survive extreme drought by entering cryptobiosis, a state of suspended life, until water returns. Over longer timescales, life has adapted to dramatic shifts in Earth's atmosphere. For instance, when oxygen began to fill the air due to cyanobacteria's photosynthesis, it was a lethal poison to many earlier organisms. But life innovated. Some microbes found ways to detoxify oxygen and even harness it for efficient metabolism, eventually leading to the complex cells that make up all animals and plants. Life turned a poison into power. This ability to not just endure change, but turn challenges into new modes of living is encouraging as we ponder life in the universe. It means that even if conditions on a planet slowly drift, life may ride the changes rather than perish. Perhaps a world slowly drying might see its life retreat to remaining seas, or adapt by going airborne as spores and seeds. A world cooling might develop life forms that generate their own heat or antifreeze chemicals. All these insights from Earth drive home a key point. If FL, the fraction of habitable worlds that develop life, is not zero, if life can get started, then nature seems to favor its persistence. The odds improve that life, once born, will find a way through the gauntlet of planetary changes and disasters. In estimating FL, many scientists argue that the hard part is the beginning, the leap from chemistry to the first self-replicating organism. After that, they suspect, life's inherent tenacity makes extinction or total failure less likely, though not impossible. Earth could be an example of this principle. Life began relatively early, and despite numerous potential calamities, has never been snuffed out in 4 billion years. That durability suggests that on any other planet where life arises, even if it faces setbacks, it might persist in some niche, waiting for a better era to bloom again. From the perspective of the Drake equation, the lesson of evolution's tenacity is that life's continuation on a planet might be more common than its genesis. If we find evidence that life took hold, we can be cautiously optimistic that it might still be there in some form, unless something truly terminal occurred. This shapes how we think about FL. It's less about will life survive once it starts? It likely will, given half a chance. And more about will it start at all, and how often? To approach that ultimate question, we gather together all these threads: the prebiotic chemistry, the planetary conditions, the potential pitfalls, and life's own robustness. With these in mind, we can sketch out a plausible range for FL. It will not be a single tidy number, but a range of possibilities, reflecting both our optimism and our caution. In the final part of this chapter, we step back and attempt to quantify the odds of life emerging on a given hospitable world, drawing on everything we've learned so far. Now we gather all threads to estimate FL, the fraction of habitable worlds where life actually emerges. It is a daunting challenge, like trying to determine the odds of winning a lottery with only one known ticket, Earth, that won. Depending on our perspective, we can come to very different conclusions. On one hand, life appeared on Earth almost as soon as conditions allowed, and it has endured ever since. That suggests that when the ingredients and environment are right, life may form readily, perhaps making FL quite high, maybe close to 1, meaning nearly every suitable planet gives rise to life. On the other hand, we have yet to see clear evidence of life anywhere else, even on once habitable neighbours like Mars. That leaves open the possibility that Earth's success was a rare stroke of luck, and that FL is very low, possibly 1 in many thousands or millions. Let us sketch a few scenarios to bound the possibilities. In an optimistic scenario, imagine that abiogenesis, the origin of life from chemistry, is a common outcome, given time and a stable environment. Maybe the universe is fertile. Organic molecules in every comet and cloud all but guarantee that any wet planet will brew life eventually. In this case, FL might be close to 100%. Every planet with Earth-like conditions for a few 100 million years ends up with microbes at least. Under this scenario, the galaxy would be teeming with living worlds, most perhaps only microbial biospheres, but life nonetheless. We might expect to detect multiple biosignature-positive planets in the coming decades if this is true. In a pessimistic scenario, perhaps the origin of life requires such an unlikely chain of events that even a perfectly habitable planet usually stays sterile. Perhaps on dozens of Earth-like worlds, organic soups form and tide pools evaporate. But the final spark, that self-replicating, evolving system, occurs only once in a blue moon, so to speak. Maybe Earth was one of the very few where lightning struck in just the right way, or near just the right complex clay surface to form a self-copying molecule. If that is the case, FL could be minuscule. It might be 0.001 or 0.000001, meaning out of a million friendly worlds, life starts on only one. In a galaxy of billions of planets, there would still be a number of living planets out there, but far, far apart. Under this scenario, finding even one biosignature will be a momentous discovery, and it may be that we are effectively alone in our cosmic neighborhood. Between these extremes lies the middle ground scenario. This view holds that life is neither guaranteed nor extremely rare. Perhaps a modest fraction of habitable planets get the spark. Some scientists speculate FL might be, say, 10% or 20%. That would mean tens of billions of planets in the Milky Way have life, which is an astounding number, yet still leaves many worlds barren. In this case, life would be common enough that with sufficient searching we will find examples, but also not on every rock and pebble. Maybe the conditions have to be just so. Not every ocean will give birth to life, but 1 in 5 might, when all the favourable coincidences line up. This scenario meshes with an intuition that Earth's quick emergence of life indicates it wasn't incredibly difficult, but the silence from Mars and elsewhere indicates it's not too easy either. What evidence can we marshal to refine these guesses? From Earth's timeline, we note again. The planet cooled, and within a few 100 million years, life was likely underway. Microbial fossils and chemical signatures in very ancient rocks suggest life was present at least 3.7 billion years ago, maybe earlier. Earth did not waste much time. That hints that a biogenesis might occur within a few 100 million years, given a stable ocean. A blink of an eye in geological terms. If that holds generally, then wherever conditions mimic early Earth, life could pop up relatively soon. That line of reasoning boosts FL in our minds. We also consider the abundance of building blocks. We've learned that amino acids, nucleobases, and other organics form easily in many settings, in atmosphere experiments, in meteorites, in interstellar clouds. The universe seems inclined to make complex molecules. This preloading of ingredients could mean that many planets start the race already stocked with the pieces needed for life. It's as if nature gives a free kit everywhere. Here are amino acids and sugars. See what you can build. That too argues that life might often assemble itself when given a wet haven. On the other side of the ledger, we must weigh the fact that we haven't yet found life elsewhere, despite ongoing efforts. Mars has tantalized us with organic molecules and maybe subsurface water, but no clear biosignatures. The outer moons have oceans, but we've not detected anything definitive in their plumes or environments so far. It could be that those places truly are sterile, meaning Earth might be an outlier after all. However, it's worth noting we have barely scratched the surface in exploration, literally in Mars's case, and metaphorically for the ocean moons. If life is sparse or deep, we might simply have missed it. Thus, absence of evidence is not strong evidence of absence yet. Another piece of reasoning comes from the anthropic perspective. We observe that life arose on Earth, but as observers, we sort of had to find ourselves on a planet where life did arise. Otherwise, we wouldn't be here to ponder it. This means our single data point is biased. We can't directly infer probability from one success, because we're inevitably sampling from a successful case. If life were extremely rare, we would still only be able to ask the question on the one planet that got lucky. This caution tempers our interpretation of Earth's quick start. Maybe it had to start quickly here for intelligent beings to eventually evolve before the sun fries the planet. If it had taken, say, 4 billion years to get going, we might not have had time to evolve complex life and ask the question. So, some argue, a fast start was a prerequisite for our existence, and might not be the norm. This doesn't give a number, but it warns us that Earth could be a special case, and we shouldn't assume every planet would copy our trajectory. Given all these considerations, most scientists comfortable with speculation place FL somewhere between the pessimistic and optimistic extremes, albeit with huge uncertainty. It could be, for instance, that FL is on the order of 0.1, 10%, meaning life on 1 in 10 hospitable worlds. If there are, say, 100 billion such planets in the galaxy, that yields 10 billion life-bearing worlds, a very optimistic outlook for a living universe. Others lean towards more conservative numbers like 0.01, 1%, which would still produce millions of life-rich planets in our galaxy. Even the low estimates allow for plenty of chances, given the sheer scale of cosmic real estate. The truth is, we will not know FL with confidence until we either discover life beyond Earth or survey a statistically significant sample of habitable planets and find them all empty. It is entirely possible that in the next few decades, a spacecraft could uncover microbes past or present on Mars, or signs of life in the subsurface seas of Europa or Enceladus. Imagine if we find even simple fossil microbes on Mars that clearly originated independently of Earth, say with a different biochemical makeup. That single discovery would immediately tell us that life started twice in one solar system, strongly implying that given the right conditions, life springs up readily. In that case, FL would likely be very high. The cosmos would be alive all over. Alternatively, if our thorough explorations of the solar system reveal nothing living beyond Earth, and if upcoming telescopes survey dozens of Earth-like exoplanets and detect no biosignatures, we might begin to suspect that life truly is a rare gem. As of now, we must assign FL with humility. Frank Drake himself, in the original 1961 formulation of the equation, optimistically guessed FL equals 1, essentially assuming that life will emerge on any Earth-like planet. Many of his contemporaries shared that hopeful view. In the decades since, some have argued for more caution, suggesting FL could be much less. The Drake equation was never meant to give a precise answer, but to frame our ignorance and guide research. In that spirit, we might conclude FL could plausibly be anywhere from very close to 0 up to nearly 1, but if pressed to make a reasonable guess, one might say FL is likely high enough that life is not an incredibly rare miracle, perhaps on the order of a few % or more, yet not so high that every pond in the universe has microbes. We can also frame it like this. If the galaxy had 1 million planets with conditions similar to young Earth, how many would we expect to actually harbour life? Our current understanding would answer, possibly thousands to hundreds of thousands of them, if FL is a few tenths or percents, or in a gloomier view, maybe only a handful, if FL is extremely low. Either way, the possibility of multiple life-bearing worlds out there remains strong. It's heartening that each year we edge closer to uncovering evidence that will inform this number. With upcoming missions and observatories, we may detect that first whisper of alien biology. Even a single positive detection, be it microbes in an extraterrestrial sample or a definitive biosignature in an exoplanet's atmosphere, would revolutionize our estimation of FL, likely pushing it toward the higher end of the range. Until then, we live in an era of educated guesses. Whatever the true value of FL, the implications are profound. If it's high, the universe may be a garden with life in many forms on many worlds, even if most are simple. If it's low, we might be one of the very few blossoms in a vast, dark wilderness, which would make life, including us, all the more precious. Either way, understanding FL helps us appreciate the delicate chain of events that led to our own existence. Now, our journey in this part of the Drake equation is nearly complete. We have reached a cautiously optimistic outlook, tempered by the vast unknown. We imagine that many planets out there have seen chemistry give way to biology, as happened here, though perhaps not all. But the Drake equation doesn't stop at FL. Even on worlds that bloom with simple life, new questions arise. Will life remain in microbial stillness, or will it evolve greater complexity and perhaps intelligence? The next factor, F sub I, beckons us to continue our cosmic inquiry. On some life-bearing worlds, life may climb toward consciousness and civilization. How often does that happen? That mystery lies ahead as our journey continues to the next part of the documentary.